What's up, guys? Tim Austin with DragBoss Garage. Welcome back for another explosive chat with Darin Morgan. So you can see he's doing something right now. So I'll do a little bit of house cleaning, we'll say, housekeeping. But I wanted to thank everybody for showing up tonight. I appreciate you guys taking the time, my family, Mrs. DragBoss and the Bossettes, for letting me have this time to spend with you guys and with Darin and his family that he takes away from his family and spends with us. So I'm very appreciative of that. A lot of stuff going on. Give a big shout out to Hammer and Hank. I hope he's watching this. Jeff Ford from Auto Restomod had contacted me, and him and I did some work together, a collaboration on some things that the 351 Cleveland are known for, or people concerned about. Obviously, the oiling and the block thickness and that kind of stuff. So look out for that. That's going to be good. A lot of stuff's been going on. I just did a video with APD, and I'm going to bring you a revelation of something that no one's ever seen in their life. Can't wait to show you that. Hopefully, Jay Zockel, you're watching this. We're going to talk. He's going to be on here for a live chat. Brent Likens is tomorrow at 6 p.m. We had an unexpected issue. I think I put 7 at 6 p.m. Eastern Standard Time. So hopefully Tuesday rolls around and I'll be able to have my engine done at Bob Beach's. I'll be down there. I'm going to hook up with Pete Reichert. He's got a nice, I think it's a 70 Boss 429 Mustang he wants me to check out, and a 64 lightweight Galaxy with that 427 high riser. So that's cool stuff. So just want to give a big shout out to everybody that's here. We already have 41 people. Darin, I want to give you the biggest thanks too, because you know what? We were talking about this. I'll tell you guys, what's crazy is I said, oh, let's test around 3 o'clock. Or whatever time it was, 2 or whatever. But Darin's camera failed. And I'm like, oh, no, not this. There's going to be a problem. You know, I already get anxious about it. So I said, but whatever. I can talk forever. And even if he wasn't here, I'll keep you guys entertained. So we finally got it hooked up and we started talking. We already talked 2 hours before this even started on a lot of stuff. So it's amazing how we can sit here and talk. And once we get going, it just starts flowing. So I appreciate that he's here because, you know, one of the things I say is that knowledge is power. And I say these things because, not just because I like to hear them, but I think that they're motivators. They help you to understand what you're doing with your engine or your combination to get the most out of it. And that's what I want to provide to you guys, something that no other YouTube channel has. It's not just Darin Morgan, but it's the whole racing thing that I can pull together. People like Warren Johnson have been here, you know, Larry Olson, you know, guys like Don Lucido, you know, tons of people. There's headquarters, you know, I'm just getting into this world through Darin. And there's guys that, I mean, he hooked me up with and guys that I've met that are just phenomenal. There's guys over in Australia that you guys probably don't even know about. Pete Murray, Tony O'Connor, Sean Burns, you know, Graham Serini, all these guys. You know, it's crazy over there. Scott Cook. So what I'm doing is bringing this information to you so that you can understand, and hopefully that's how we present it. So we said, what are we going to talk about, Darin? It's been, let's see, it's been 11 months. Let's see, I wrote it down. 11 months, 1 year, 11 months, and 9 days since we last did a live chat. It's like, oh, yeah, we'll do it in a couple of months. Yeah, I'll call you. But you know what? Everyone's lives are so busy. You know, we got 60 people here spending their time. They're probably like, Tim, enough talking. We want to get into some chat. So we do have a couple of things that we're going to do. One of them is going to be some technical stuff. And I think this is something that all you guys need to understand if you're going to watch people like Eric Weingartner. You know, he does a lot of head porting, you know. So these are things that I kind of know how they work, but I don't have a good handle. And if I don't understand, I'm not afraid to say, Darin, I don't get this. Can you explain this to me? So one of the things I wanted to talk about was measuring cross-section in a cylinder head in the port, because I think you need to know that area and how fast the air is going through there. Those are the things that help you calculate the power. So I had talked to Darin about that as being one of the first topics we talk about. Now, you guys have a lot of questions here. I see a lot of people here. Eric McMahon, thank you for being here. Dean Stevenson, AC Collins, thank you. Marianne Liano, thank you. Let's see who else we got here. Bob McAllister, Jim M, Diane Bree Garage, all these guys, R.W. Falco. So thanks, guys. So with that, Let's enter this world of airflow dynamics with Darin Morgan and talk about cross-sectional area first. What can you say, Darin?
Say what?
You're
going to leave it up to me?
Yeah. Well, you know what it is? It's always like, you try to figure out what can this head produce for horsepower. The thing we use is we use CFM, and they do the calculation. They say, yep, you can get this much horsepower out of this much CFM. But really, how does this cross-sectional area flow into that calculation? Where's the timeline of this? How does that fit?
Well, if you're going to design an engine from scratch,
yeah,
you're trying to hit a target horsepower, you kind of go in a little circle. First, the bore dictates the valve size.
Okay.
And that valve size will dictate how much flow, and the cylinder head design will dictate how much flow. Now, with a given size valve, with a given size or design of cylinder head, I know how much that's going to flow. So let's just say that if I had a 4700 bore and a 2550 valve, I know I'm going to move 550, or the maximum you can get out of any valve is about 118 CFM per square inch of valve area.
Okay.
That's about it. It doesn't matter. So what it is, that's all you're going to get until it hits about 1 and you get into the secondary part of the discharge coefficient, which is another story. But let's just say 118 CFM per square inch of valve area. So that's my target. Now, my job is to make that valve flow efficiently. And this is where people will get into flow benches lie to you. Well, yeah, flow benches allow us to lie to ourselves because we're not looking at all the other variables involved. We're just looking at those CFM numbers. But it's not just CFM, it's CFM per unit area. How much area do I have for the flow that I have? That's velocity.
Yep.
So I have to make that area as efficient as possible. So if I don't make it efficient, I'll never reach the potential of that valve, even though it flows 555 CFM, and that's capable of 1,350 horsepower. If it's a pig, if it's slow, if it's inefficient, it's going to be 100 horsepower off. So that's where airspeed comes in. Airspeed is a variable you use with CFM to gauge the efficiency of the system all the way up through there. So the bore dictates the valve dictates the flow, and everything upstream of that valve from that point on is a ratio or dependent on that valve and how efficient it is, meaning the areas that I use to get the velocity that I need.
So the limiting factor is the valve head.
The limiting factor on almost any engine is always the valve. Yeah.
Okay.
Unless you're getting into 4-valve stuff, and that's
right. Yeah.
2-valve stuff, yeah, definitely.
Well, then, just to throw a wrench in the whole discussion, not that we're going to go on this tangent, but now if you look at a boosted application, then is the valve size, the head, is it still critical?
Same thing. Yeah, same thing. Still critical. Now, it's a little less critical in certain areas. You can run it a tad larger, maybe 5%, depending on the fuel, whether it's alcohol or gas or what have you. What the inlet temperature is means when on boosted applications, let's say if you boosted it to 2 atmospheres, if you're at 14, 28 PSI or whatever, or 14.7, 2 atmospheres, and the inlet temperature is 200 degrees, you're not gaining anything because all you did was stretch the molecules out and heat it all up. With the boost, you don't have anything. The idea is to keep the temp down, and then the velocities stay the same, which this is one thing that people got into a long time ago. It's like, well, if I am running 2 or 3 atmospheres, if I'm running 50 pounds of boost, I have to make the port bigger. No, you don't. It's still the same amount of airspeed. It's just you're cramming more molecules into that 1 cubic foot that's passing through the port.
But if you're heating it up, then the density.
You're making it less dense, which heats the port.
Spread out. So, okay. Yep, I get it. Let's. So measurement. How do you? I would say a rectangle port big block Chevy. It's pretty easy when you got it's square. I would say, right? I think it gets complicated when you have oval port intake.
It's height times width. If measuring the opening of the port or at the push rod area is usually pretty simple, because that's not a complex geometric shape. That's just an oval or a square, and it kind of holds that shape for a while. But once you get past that, a lot of these ports are twisting.
Sure they are.
The walls are converging, so you have a really weird shape over the window area, and you can't measure that the same way. But we'll get to that here in a minute. I gave you a little sheet there.
Yeah, you ready?
And basically, it's height times width minus the radiuses, and it's so easy to find the radiuses. Let's say we have, if you look at the port down there, that's 2.5 inches tall and 2 inches wide. And the calculation there in the middle is 2.5 times 2 is 5 square inches.
That's it.
And then you have to get the radiuses out of there. And if the radiuses are equal from top to bottom, you just take the diameter of an 800 radius, which is 1/6. And then you just take the circle minus the square, and you got it. So it's 1/6 times 1/6, which is up there in the top, is 2,560. And then 1/6 diameter squared times 0.7854 is 2 inches. So all 4 of those corners take up 0.550 square inches. And then you just take that off of the total of your height times width, and that's your area.
But how far in can you count that?
That's just in that plane.
Right.
Yeah. That's just in that plane that you're measuring. Sometimes, if you have a little bit of a twist or walls converge, what you can do, or what I do, is I take a top measurement and a bottom measurement, divide it by 2, which gives me the middle, and do the same off of each radius. And then that's my height and width, and then calculate each radius. I have a whole bunch of valves that I've turned down of different radiuses that I just hold in the port in any one spot. So I can gauge, because the roof radius gets bigger as the floor radius gets smaller going into the port.
Yeah, I can see it in my mind. Yep.
On a lot of ports, the roof is just one big radius, and the floor is, it's like this.
I love to see how they sometimes twist them right down. You see the
got half-inch radius on the floor and 2-inch radius on the roof. And you just hold your valves in there, and okay, well, this is a 2 here, and this is a 1.5 here, and this is a 650 here, and this is a 675, and then you just work it out. But that's the old way to do it. That's the rough measuring way. That is a rough measurement. That is not exact. I mean, you can be a 10% off pretty easily trying to do that.
But is that the way they've always done it?
No.
This?
Back in the 90s, up until I think 96, when we got some DOS software that did it for us, what we used to do is take a rubberized mold.
Now, who are you working with then? Where's this at?
That was working with my dad and with Glidden, and we did the same thing at Larry's when I was there.
Okay.
That was in Larry's. At Larry's, that's the first time I ever used DOS software with a printer, which I'll explain here in a minute. But what you do is you take a rubberized mold. There's lots of mold compounds you can use. GL 2000 is what I always used to use, or GL 1000 rubber. And then you would take that long port and slice it every ½ inch along the center line of that port, and then take 3/32 graph paper, plop that on there, and trace it around with a fine pencil and sit there for hours on hours. It'd take half a day to count the little squares to get the area for that particular place. And you do the whole port that way. And it usually takes about 4 or 5 hours to do a port that way.
Can you imagine Glidden? Come on, Darin, what are you doing? We got to hurry up. We need this. What are you doing?
And then later on, and I don't know who wrote the software. I think it was Kevin Grundig, the same guy who coded Engine Analyzer Pro. In 1994 or 5, he came out with a software program where you could set the scanner on the printer at 600 DPI, 600 dots per inch, set it on there, and then download that file into the software, and it would count the 600 DPI. It knows it's 600 dots per inch, so it would figure out that area. And that was accurate to within about 2-3%.
Nice.
But nowadays, it's as easy as bringing up the CAD model and splicing it anywhere you want and finding whatever area you want. And, there's not the whole induction system. You do that for the whole intake tract.
Right.
And then you get an average, because if you take your volume over length, you're going to get your average cross-sectional area, and that's your average airspeed. And with CNC machines, you could get it accurate to within 0.5%.
And then can you confirm that with like a pitted tube to see?
Well, no, you can't, because the average airspeed and the dynamic airspeeds in the system are completely different, because you're going to have 260 on the roof and 380 on the floor. So they change drastically through the system, because no matter how much bend you have, the air sees a straight line right to the bore. So the highest air speeds are usually on the roof, on the tip of the short side, and across on this plug side of the chamber.
A guy asked me a question, and let me see if I have it right here, and then we'll start asking some questions here. But he was talking about, laminar airflow versus turbulent. That's Jim Mueller. Laminar airflow versus turbulence. Because we've talked about this, that engine is moving back and forth. There's harmonics flying. There's all kinds of different forces and heat and all that. It just doesn't give you all that stuff.
You have to take all these dynamic events separately. I mean, first off, repeat that question one more time.
How do you correlate between laminar? We think about laminar airflow with a bench.
If you're the first thing is there's no such thing as laminar flow anywhere in an induction system.
Okay.
If you look up what's called Reynolds numbers, REYNOLS, Reynolds numbers, a Reynolds number is a measure of, I want to say the chaos, but the turbulence in a flow past laminar. And if you do some research on this, you'll find that any tube, depending on its size, has its laminar point, which is at a lower velocity. But once you start getting into higher velocities, you will get into turbulent flow, and there's no way around it because of the shear forces of the boundary layer and everything else.
Yeah. Yep.
So a Reynolds number is a way of rating how much turbulence there is versus that laminar baseline. So usually in an automotive engine, you'll have Reynolds numbers of 2,500 to 4,500, depending on where you're looking at. Now, that doesn't mean a whole lot unless you go study Reynolds numbers, and you'll find out that that's not really that turbulent at all. We don't really consider that turbulent flow. But if you had laminar flow in an engine, that would be pretty cool. But there's no way to do that, because we have to turn it out of the carb, we have to turn it into the runner, we have to turn it around the short side, and then we have to turn it around the valve. So there's way too many places to instill turbulence in that system.
All right, I hope that answered your question. There's a couple questions. Let's see if we can get some here. Here's one here. Let's see. Find the right beat. Would a basic seat combination of 36 degrees, 45 degrees, 67 degree, 80 degree blended into the throat be effective for achieving optimal performance on the intake side of a Honda K24? Appreciate if you can provide your input. No clue on that one.
When it comes to designing a seat, valve, venturi, chamber, bowl combination, which they all go hand in hand, the flow around the valve is governed by 1 inch below that valve and 1 inch above it, not just that seat. That seat, that venturi section that you're tuning up there, can change depending on chamber angle, depending on how the port approaches the seat, whether it's laid way back or stood up or has a hard bend in it. All that will affect that seat tuning and the angles that you utilize in that seat throat combination. So it is impossible for me to tell you if that is the proper way to do it without knowing what back cuts are on the valve, what back angle radius and the back angle and radius, what those are. Is it a heavy tulip valve? Is it a flat valve? what are the back cuts, what are the widths of the back cuts, how much margin I have, what are the chamber angles. I have to know all that and then test it on the bench myself and then get a velocity probe in there and then figure out, listen to it, see how efficient it is for the area that's there before I can say, yeah, there's more. In other words, there's more than one way to skin a cat, guys. There's more. That seat will work if you, let's say on a 36, that's fine, a 36. But what happens if your chamber's at a 40? Well, you change that. Well, now all of a sudden, this makes a lot more sense. The 36-45 and then the 67-80 makes sense with a steep wall, where because the seat underneath there, the chamber is stiff, you want the seat aimed up. So you're cutting your back cuts steeper to aim it with the combustion chamber. But if you had a 60 and a 70, you'd be aiming into the chamber, which is not exactly what you want most of the time. So basically, you're treating the whole system as a venturi, 1 inch below the seat and 1 inch above it, that whole thing. And those seat angles all tune all that up, along with the back angles and the back cuts and the radiuses and everything else. Now, the general rule of thumb with any seat combination is don't turn it any more than 15 degrees. Simple. So it'd be 30, 45, 60, 75. Boom.
Yep. That
is the basic seat. And then from there, you can modify it. You steepen the chamber and you can go from a 35 to a 40 top cut. Now you're a 40, 45, 60, 75. Well, what happens if it's you go to thinner back cuts on the valve? You can't utilize the valve to help turn the air. Well, now you're going to run a 60 and a 75 that's wider to help turn it into the bowl, which is going to choke the throat down because now you've made the throat smaller. So if you run a back cuts and the valve designed properly, you can make the throat bigger and use a 65 and an 80 and aim it straight out and have the valve itself help turn the air around and make your throat bigger and pass more air through the system. Basically how it works.
So the angles are changed. Now let me get this because I didn't really think about this, but so the valve angles can be changed depending on the direction of the port coming in.
And the chamber. Yeah.
You might
and
want
the valve being
valve angles, right? I mean, I always think, oh, it's got to be 45, whatever it is, 55, whatever. I don't think about that. I don't think about you can bend that and change that and direct it. That's wow, that's cool.
Yeah, and that's where pressure recovery comes in with the combustion chamber, because on low lift valves of 500-600 lift, you can use like a 45 and a 30. A top cut's really laid down, and then your chamber kind of comes out. But once you exceed 600 and you get into the 750, 800 range, that combustion chamber starts coming up and the seat starts coming down. And now you're using the actual chamber itself as part of the seat.
To manage the air. Yeah.
When the valve pops off the seat, it needs to see an ever increasing area. If it pops off the seat and sees instant area, it goes turbulent. Can't control it.
Controlled and
yeah, that chamber angle is control.
Yeah.
That controls because it needs to see all the way around. So if your valve's deep in the bowl, you need the same angle on both sides. If you lay one side back too far, you're going to offset. You're going to offset it, and that's can be an advantage on some chambers. You need that because it doesn't have any flow over there, and you can lay it back, and you can get a little more over on that side.
See, this is the stuff that
it's all application specific.
I dig. I can see it, and like I said, we got 81 people on here, guys. Thank you for being here, and if you guys ever contribute any super chats, all the money's going right to Darin for him taking his time for DragBoss Garage and you guys. So if you contribute, it goes right to him. Now, these are concepts that I no one talks about this stuff. I don't know any other channel that has headquarters on there other than guys that do it themselves that can explain it like this, because you just it was like a revelation right there for some reason. I guess I missed that concept, but now I got it. So thanks, Darin. Here's this one. If Walmart sold Darin Morgan pajamas, I would wear them to bed every night. Well, you know what? We could take care of that because we'll have DragBoss Garage pajamas and Darin Morgan. Our merch is coming out. We got a bunch of these coming out. Cool stickers. Yep, it's coming. I'm just real.
You brought it. We were talking earlier, and you were talking about airflow through the port.
Yep.
And the harmonics.
Yep.
The pulses, the bounce back and forth.
Yeah.
All that stuff.
Well, because I was at APD yesterday, and I did a carb tuning video with him, and we talk about this. I know you talk about pressure recovery all the time, and it's like, Jesus Christ, I hope it's what I'm thinking it is. Sometimes I don't ask questions because I don't want to look like I'm an idiot, but sometimes I just, I can figure that out. But we talked about this with the Venturis and a carburetor. When you nail it and drop those throttle blades open, man, you got air that's 14.7 pounds per square inch that has weight density above that carburetor. Now you got a pressure drop. Boom. Now it's pulling it down. That piston's coming down. That stroke's coming down and pulling that in there. That's where the velocity comes from. That's where that pulls that air through the Venturi. So that pressure drop, until it catches up with the main system, I mean, that's where you have that pressure drop, just like shifting you talk about.
And it's not instantaneous. So this is why carb spacers with a 7-degree taper, they control the pressure drop into the combustion chamber or into the plenum just a little while longer and let that air slow down before it gets into that open space. Because if air just goes into an open space, it just goes turbulent and it chokes down the throat. Okay. So you have to have some form of deceleration of that air to control it. And that the airflow just goes up, 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 the more control that you have over that. But you brought that up. It takes time, milliseconds, but those milliseconds get longer when you shift the engine.
Well, you're putting the clutch in, okay.
You've got the whole system wound up. You've got all this airspeed, and all of a sudden the engine goes boom and drops. What happens to the airspeed? The airspeed stalls down too.
Oh, yeah.
And then you shift and want to reaccelerate. Well, the airspeed's coming down. The engine's trying to come up. Well, guess what? You get a lean spike. That's what causes the lean spike, is that lag point. And the whole idea is to get the plenum size, the carburetor size, and that pressure recovery zone just right to where when you shift, it comes, it comes right down to it and goes boom, right back up with it.
My car drops 1,200 RPM on shift. When I shift, drops 1,200.
Okay. Like an automatic will drop 1,800 or something like that. And they're worse. They're harder to manage. That's why you have to run smaller plenums and smaller carbs on automatic stuff than you do on stick stuff, because you don't drop as far. And this is what happens when you put too big a runners, too big a plenum, too big a carburetor on an engine. That lag point, as soon as the engine stalls, the lag point drops down, and then the engine tries to come up and you get a lean spike. It can't get back up with it. Yep. You need instant recovery on the shift. On the dyno, you see it all the time. It's all the time. You put a bigger plenum on there, it makes more power on the dyno. You just keep stacking spacers, putting bigger carburetors on there. It'll make more power. You take it to the racetrack, it'll burn a piston up when you shift it. It'll lean out so bad.
Wow.
So that's why I say there is no calculation, hard calculation, general rules of thumb, but no hard calculation for plenum volume. That is a track tuning deal. It can only be tuned on the racetrack.
So, I mean, think about it. If you get too big of a plenum and you put that spacer on there that kind of does a Venturi effect to kind of tunnel it down, so it kind of can compensate for too big of a plenum volume.
A lot of these spacers nowadays, it's a hit and miss deal, because you don't know what that plenum wants. You don't understand until you get on the racetrack what it's really telling you it wants. Now, the dyno will give you indications.
Sure.
So you'll try all these different spacers, extended ones, and, ones that we do. I designed at Rare Morrison actually have what's called a pressure trap. In other words, they come out like this, and the barrel sits down in a hole. So the air has to come out of the barrel and then go around into the plenum. So there's this low pressure area. The velocity from all those barrels forms this low pressure area. So when the pulse tries to act on it, it absorbs it in that cavity, and the barrels just keep pumping fuel. So it doesn't act on the booster. And that's what's good about EFI. You don't have to worry about this. You can run as big a plenum as you want, as big a throttle body as you want. And the only problem with running too big a throttle body is you can't stage the goddamn thing because it tries to gain too much area and the engine wants to just gain RPM too fast.
Yep.
But EFI solves all those problems. And as a matter of fact, on the shift, you can shoot more fuel to it if you want.
Damn. See, this is what I'm talking about. We should get talking. I don't even know how long we've been talking now. 30 minutes, a couple hours. All right.
I do know of some pro stock engine builders that still dyno the engine with carburetors because they're probably like me.
I know they do.
A carburetor will tell you what's going on. EFI won't. It won't tell you. All you're doing is band-aiding shit for power. You're just messing with the tables and trying to put more fuel in areas.
Compensate, right?
And you have your lambdas and your fuel table, and that's your two things. But a carburetor will tell you lag. It'll tell you how bad the lag is. It'll tell you if you're getting vibration in this. It'll tell you all sorts of things that EFI will just completely cover up.
That's exactly what Frank Iaconio told me. He hates fuel injection. He loves carburetors. Wish they'd go back to it in pro stock, he said.
The only problem with carburetors is the uniformity of charge. It is never consistent. There's always some variations in there or hiccups in there. The fuel floats in the bowls. Wait
a minute. You're saying between each carburetor by one manufacturer, say, right?
Yeah, and either the G-forces acting on the carburetors change the fuel curve. So you're going to get lean spikes and you're going to get into trace detonation far sooner with a carburetor than you are EFI. And like on a nitrous engine, that was just instant death. I mean, the engine would just go pop, gone, and now with EFI, that doesn't happen near as much.
All right, here we go. Ready? Mariano Leonel. Hi, Tim and Darin. Darin is a real genius. I saw all of his videos, ton of time. I'm from Argentina and really appreciate that he shares his knowledge. I would love that Darin make more videos. You know what? We were just talking about that. We're not going to let the cat out of the bag, but stay tuned for that one. Trust me. Okay. How about this one?
I wonder if people would want me to do a series of videos of maybe, I don't know, 15 or 20 hours on everything that I know and show every math equation for every instance and run through 350 to 500 cubic inch to 700 cubic inch motors. And
that's the plan, boys. We'll have it right here at DragBoss Garage. We'll have a little area. We'll have a private section that we can join. We'll figure that part out. We'll have a private little thing where we can have seminars with Darin alone. Maybe 10 or 12, however it works out. Good idea, Darin. Great minds think alike. How about this one? I live 10 miles from Bischoff Engine Service. Nice hat, Darin. Joe Bradley, go down there tomorrow. Nope, they're closed on Sunday. Someone will be there. Go down there on Monday, bring them all coffee, send me the bill.
Don't forget the donuts.
That's it.
Really big on donuts.
George Drace, hey, how about Darin sharing some cylinder head math related to valve diameter, throats, velocity, etc.?
Okay.
You know what? We would do that on that section. We could maybe share a little here, but that's what we'll do. We're going to have a little playlist or a private area.
It would be very difficult at this point without putting together a presentation on that, the complexities of all that math and how it interrelates. But again, going back, the cylinder bore itself is what dictates the valve area that you're going to get, the maximum valve area. And I always use the general rule of thumb. And when I talk about these general rules of thumb, the 90% rule on the throat, valve sizing, these are general rules. These are starting points. And people have taken them in the past and used them as gospel. They're not. They're just starting points. Okay. But I will say that you're not going to get any more than 3 or 4% either way off of that point and do anything with it. Okay. So the bore itself will dictate the valve will dictate the flow will dictate the power and RPM and the given engine combination that you're dealing with. So if you have a bore that's 4 inches and it's a wedge versus let's say a canted valve, you can put a bigger valve in a cannon valve head and maintain high efficiency. So for a wedge, you're looking at about 50 to 51% of the bore. Can you shove it up there? Yeah, you can go to 52, 53, but the whole cylinder head design has to change. At that point, and we're talking like a competition eliminator.
Yeah.
320 cubic inch to 350 cubic inch motor, where you have to be able to turn 11,000. So you need a 225 valve in this thing. And the only way to do that is to shrink the exhaust down and move it against the wall and manipulate things to try to get that in there. That's very, very difficult to make work. And that's the challenge. That is the challenge, is to get that valve, get as much valve area in there as I can, and maintain high efficiency. Still get 118 CFM per square inch of valve area out of that thing. Because again, if you have a lot of valve area and you don't have a high efficiency, you will never reach the potential of that valve. And this is where the flow bench allows us to lie to ourselves when we're looking at CFM numbers alone.
Right.
You know, and
that's what sells everything.
Yeah, it does. But the efficiency of that valve is going to dictate whether you can reach the potential of that valve.
Mm-hmm.
Like if you look at a Pro Stock engine, for instance, the RPM at which they make peak power is tuned to that valve flow and efficiency number. So if I have 625 CFM and I have a high discharge coefficient, I know that I can make peak power at 10,100 RPM with that engine. But if I have a lower efficiency on that valve, I'm not where I need to be. It'll never get there. It'll never get there.
But if you say you want it at 10.1, okay, are you going to shift at 10.5? Yes,
you should shift it.
Yeah,
600 to 800 over.
Now, can you use that rule of thumb, so to speak, for these guys that have street cars or 11, 10 seconds, all that?
That's pretty uniform. 600, for a street car, probably about 500-600. There are instances and rare cases in which it's 1,000 or 1,200 over, but that's That's NA unlimited engines comp Pro Stock stuff. You could. Back when they were shoving the RPM ranges up.
Yep.
They were doing a lot of things. They were upping the weight compression ratio really high. So when the VE started falling off, they could hold that over rev out and just carry it out. Just keep carrying it out. So they can move the whole power band up and fall into more power. So let's say you're making 1,300 horsepower at 10.1 and you got 1,200 horsepower at 10.8. Well, if you make 1250 at 10.8, instead of dropping back to 8,500, where it's only got 780 foot-pounds of torque, let's say 1,250 horsepower, you can drop it back to 8,800, where you got 1,300 horsepower. So now you've averaged more horsepower in the band by moving that up, but you have to have that overrev. You have to maintain the overrev for as much as you can. Hold that power.
Okay, yeah.
The overrev is so important. It is so important.
It's amazing. 100 people already. So that's nice, guys. Thank you for being here. Let's see what else we have here. Thanks, George, for that question. Let's see. Shrammy21. Good shout out to Tony from Toka here in Australia. Absolute small block Ford beast. Does great work. Yes, Tony O'Connor from Toka. Now, one of the things that they are, here's what I'll tell you about something. This is what I learned about certain head porters. They're called quiet achievers, especially guys from Australia, because I've tried to get them on to talk with them. No offense with you, Darin, because I want to bring anyone I can to talk airflow. So I talked to these guys, but a lot of them they're shy. They're humble people. They have a hard time. They don't want to talk and spread their secrets, or they don't want to talk in front of crowds. So
you think this is easy for me?
I bet you, it's not easy for me. I get anxious. I was like, when I start out, that's why I'm talking so fast. My adrenaline's pumping. But it takes a lot to come on here and talk and explain these concepts that are so difficult for most to understand and break them down into my level.
You know me, I'm I'm at work. I don't say 10 words to anybody all day.
I know.
I got my blinders on. I'm working, and I don't like interruptions. I hate interruptions.
Yep.
But that's business. You're going to be interrupted from time to time. You got to solve the problems and move on. But when I'm in the zone, I don't like to be interrupted. So I'm one of those quiet guys that just works, and I guess that's the way I've always been. But I'm also pretty high anxiety. So
yeah,
it's like we had this scheduled last week, and I was like, man, I ain't feeling it.
Right, and if it ain't right, we don't do it. That's what I said. I don't care about this. Plus, we have our families come first. This stuff is fun, and some people, you make your living with it. But my family comes more than any of this stuff. This is just stuff. The best things in life aren't things.
I have to have everything lined up one day, and I never practice. I never do any of that. What I do is I line everything up I need to do one day before I come on, and then just talk off the top of my head.
And I'll tell you, boys, 105 here already. We haven't even nipped the bud. Let me tell you. We'll get to this in a little bit because we're having so much fun now about his presentation, which will be pretty darn cool. But I wanted to answer some of these questions you guys have. So it does give you a little anxiety. When you come on there, I had Warren Johnson on, and his camera there's an issue with that. And we worked on it right up until I watched that clock count down to 30 seconds. I'm like, all right, Johnson, you got this yet or not? And he's like, I can hear you. I said, that's all that matters. Let's roll with the show. And that's what we do. And it is a lot of thinking off the cuff. And I put you on the spot with a lot of these questions. And we've said before, if you don't know or you don't know, you just say, I don't know. Here's one for you. Let's see. This is Ralph Martinez. Hey, guys, I have a question on camshaft lobe separation in relation to valve placement, like inline valve placement versus canted. I dig it.
Okay. Well, oh boy, you're dealing with a dynamic situation that is really interdependent on a lot of other things. But there's some general rules or things you can draw from this. The amount of overlap you need is tied to not only the timing requirements, the opening and closing events, and the lobe designs that you choose, but it's also tied to the amount of overlap flow that you need to move air through the engine to make power in the band that you pick. So down low, when you have down low RPM, and we're talking 1500 to let's say 7,000 or 6,500 RPM, low RPM, street stuff, Normally, what you would do in the old days with the wedges and everything, you'd have like 104 center line. You'd have, a lot of overlap. Mm-hmm. The LS3 heads breathe what we call cross flow, or what Maskin called chambered draft, very well. So they move air from the intake out the exhaust, so you can widen the lobe separations a little bit, 2-3 more degrees. And then to keep the overlap down for EPA, fuel mileage, they widen them even further. Now, a stock LS3 has negative overlap. It has 0. And that's to keep any of the fuel airframe mixture from going out. Well, racing engines don't operate that way. Once you hit 10,000, having, 50 degrees overlap, 48 to 52, 54 degrees overlap is common. And the more those valves, like a wedge, when that intake opens, this air has to come out and come around. So when you turn those valves around like a Hemi, the air goes in the intake, right out the exhaust. It has all the overlap flow in the world. And I've got a whole presentation on this. Where did I do that thing? I think I did it at CAW. That has all the valve positions and the cross flow. Right.
As you rotate that valve, the RPMs go up higher, right?
Yeah. The ability to make power higher and higher is easier to achieve, because it's like a Hemi wants to wind to the moon. It just wants to keep going. But you also have overlap depletion with a Hemi. So the lobe separation, or the amount of overlap that you have, becomes a little hypercritical, because if you have a little too much, it kills the torque. If you have not enough, it won't. The power band goes flat. But this is where we started rotating valves. And in 99, I did the first RM26 engine for Rear Morrison. Those cylinder heads had more rotation than what they had, less port height, smaller valves, and everything else. But the whole system tuned up, and they went right in the show. Since then, after that, we built 2 engines a year. And what we did was we took one engine and we clocked it just a little more. Clocked it. Just every year we clock it. Pretty soon on the DRCE ones, I had the valve hanging out over the valve cover rail. I had to weld the whole side of the head out because the valve spring was hanging out over the valve cover rail. And what we saw, this shows you how dependent engines are on their valve train and the available technology that we have. Because back then I had a set of cylinder heads that were almost within probably 10% of a DRCE3 now. We had 55 millimeter cams. We just went to a 60 millimeter cam. We weren't even, past the 1-inch 50 lift number. We did not have control of our valve train. And the RPMs were like 90, peak power is like 9,200 at the time. So what happened was, when I did those heads, we put them on the engine, and it was a complete freaking disaster. It knocked 25 foot-pounds of torque out of this motor. I mean, it was horrible. Well, we just like, well, stick a fork in those. So I stuck them on the shelf. 3 years later,
should have ran
55 millimeter camshaft at 1080 gross lift and control over the valve train. Put those heads on there, they were 40 horsepower more. So that's how dependent we are on the valve train and everything else.
Right.
And let's put it this way. We had an engine that made 1,300. Yeah, it made 1,380. And that was with a 60 millimeter cam. And the smaller, they didn't have the wheel guided lifters, or Jessel didn't have any of the fancy shit they got now. 5 years later, we took that, put a 65, or I think a 68 millimeter in it, put the 1-inch wheel, 1/220 wheel guided in there, and we didn't do anything else to the engine. That was it. Just the valve train. 40 horse. That thing went from 1,380 to 1,420 like 8, just like that. The same heads. Same manifold, same everything. That's how important the valve train is on a high RPM engine. And now that we have the technology, thank God for Jessel and Billy Godbolt, because if it wasn't for those two, we wouldn't be able to wind these things up like we are. And with those valve trains, it makes everything else I do not just more important, but more reactive.
Right. I can handle it. I get it.
I can make a small change. It's like right there. It's like, this should do this. And it does that. That wasn't like that back in the 90s. You were trying a lot of funky shit, and it just wasn't doing what you thought it was going to do.
You know what Frank Iaconio told me the other day? Or he was saying something about, he said, if you can't see 1 or 2 horsepower on a dyno, then you ain't making no changes. And
see, at Rares, the air system for that dyno is the air system from an operating room. It's constant 2,800 CFM. So with 2,800 CFM constant airflow, but what it does is it takes the ambient temperature, cools it down to 40 degrees, wrings all the moisture out, turns it dry and cold, then it stabilizes in the tunnel up there. For you introduce a mist until it takes 25 minutes to stabilize at 50% humidity. Really? So no matter what day we dyno, it's 70 degrees, 50% humidity, no matter when. The only thing that moves a little bit is that barometer. So our correction factor is like 1.02. That's when you can tell 1 horsepower difference. But also, you have oil temp in out, you have head temperature front to back, you've got all these sensors, and on the dyno console itself, you have bar graphs set up, and you have a bar on that graph.
Yep.
And if those bars, say the engine temperature gets too hot, it'll go into the red. The oil temperature goes up 5 degrees or 10 degrees. Well, that's a horsepower right there.
Yeah.
You can't make a pull like that. You have to have all those variables come down into that bar and settle, and then you walk into the handle. And then you can tell 1 horsepower difference. You have to make your variables stable, or you're not going to be able to tell a thing. Now, let's put this into context.
Yeah.
Okay? You're looking at a 1,400 horsepower engine. 1% is 14 horsepower. You're trying to tell the difference between 1/10 of 1%.
Right.
That takes a lot. That is a challenge, and it takes a lot of attention.
It's amazing. You know, hear that. I can just hear that thing screaming, 10,000 RPM pulls. Wah! All right, let's see here. Just to go off on that separation angle, as the head's flow increases and is more efficient, then you widen the separation angle, correct? So, if you got
it's a balance between the valve positions, how well the engine breathes, cross flows, and the RPM range of the engine. So lower RPM range will want more, and a higher RPM engine will want less, relatively.
Okay.
Yeah.
Let's see here. I'm happy. I know there's a bunch. We've been talking so much. I've been missing a few. So let's come up here. Let's see. Here's one here. Hey, Ed's Machine. Thank you. He's a good guy. He's got a great YouTube channel, guys. Check him out. He's into doing a lot of machine work. I've watched his 427 Chevy stuff. So thanks for being here, Ed. Bill Fioretti. Thank you. I've seen many builders go for high lift flow and pay little attention to the low and mid lift numbers under the curve, velocity, swirl, etc. Sets the table here. Darin, thoughts on this?
Okay. All of those criteria have their place.
Street.
I think Richard, when I was talking with Richard Maskin, I asked him basically this same question, phrased maybe a little differently. And I'm paraphrasing here.
Okay.
Basically, I said, what's more important, low lift flow or high lift flow? And he looked at me and he went, it's all important. I said, well, where should it flow the most? He goes, everywhere. It has to flow everywhere. What are you talking about? And I was like,
Maskin said this?
Yeah, he's right. He's right. Because if you concentrate on low lift flow or high lift flow, you can achieve the best of both worlds. Now, granted, you're gonna take a little hit in the mid range, maybe 5-10 CFM to gain that 30 or 40 up top. But the whole flow curve, depending on your valve lift, what we call it is jumping up on the flow curve. That's what we call it. How fast it jumps on the flow curve.
Okay.
So if you have a 500 lift valve, you want it to jump on that flow curve and flow as much as you can before it starts leaning over. Okay. Or in a perfect world, a straight line. You just want it to keep gaining. But there is no scenario that way. And you can tune ports to completely nose over and go turbulent at 700 lift,
right,
and build a huge, big, it jumps up on the flow curve, but it'll go past that, it goes negative. It'll go turbulent and everything else. But within that lift, it has a lot of flow area, or a lot of flow, period. As the lift climbs, you have to start taking that and kind of straightening that out and continuing that up. So where, let's say you'd have 145 or 165 CFM at 200 lift, you drop it down to like 140. So you're going to take a 10, 20 CFM hit down there. But what you're doing with higher lift cams, we're through that range so fast that we can take that hit and we can build more flow from 4 on up.
Right.
So it depends on the lift of the valve. The curve depends on how high you lift that valve. So you can tune the flow curve for any lift curve. That's easy. I'll show you some flow numbers here later on the new Assassin cylinder heads.
Yes.
And I thought when I did the Raptor cylinder head that was the most efficient cylinder head I'd ever done. It was the most efficient port I'd ever seen. CFM per square inch of valve area. It was ungodly. And I thought I'll never top that. But I did manage to do that on the Assassin heads. It flows everywhere from start to finish.
There it is. And I'm making a video on those heads right now, all the ins and outs of them. And Darin's already been working on them. So this is kind of nice that this ties us in.
And the reason, by the way, the reason you can do that, the reason I could pull that off is because of the design of the cylinder head. On a wedge cylinder head, let's say if you put a 1-inch lift cam in a wedge cylinder head, you're going to take a more of a hit in the low lift portion of that flow curve to build the high lift because the valve is so inefficient to begin with. With a canted valve or a Hemi, you don't have to take any latitude. You don't have to take a hit anywhere because it's got a perfect pressure recovery area, and you can tune that system up to where it balances top to bottom and flows from start to finish. And the Assassin heads have a lot of rotation. They have a really beautiful pressure recovery area.
I can't wait till we get to that. The 372-6548, baby, Cleveland. Hey, thank you. G. Isaac, 1999. Thank you. So that's for Darin. Hey, Darin, love listening to you and appreciate your knowledge. Thank you so much for your time. Tell Mike Weiner hello from the Bear. V4. He'll get it.
I will tell Mike that. And by the way, Mike is a very talented engine builder.
There it is.
I love working with him.
Big shout out, Mike Weiner. Don't know you, but maybe we can get you on here and talk engines. All right, let's see here. Now this is good. And again, RIP Dan Jessel. You know, I recently read an article about Dan Jessel's Equal 8 engine project. Did you ever have any input to it? The head looks similar to that perfect Ford Pro Stock head you did from an earlier chat you had with me, Tim, DragBoss.
The only thing holding that engine back from making more power than anything I've ever seen is R&D and money.
So, Tonto 2009, let's get some collections up. We'll get that thing going. Thank you. Benjamin Crouch, hi from Australia. I hope you guys are having a good time down there. I think it's pretty early in the morning down there. Here's again. Find the right beat. Thanks, Darin. We appreciate that. Aaron McMahon. Darin, can you give me a suggestion on how narrow I can make seat widths for valve seats without making them too narrow?
Yeah, this is always a point of contention. And it depends on the seat material and valve material, whether you're a bronze alloy and a titanium, or titanium that's coated or non-coated, or steel on iron, or titanium on iron, God forbid. They all take a little different approach. Let's say normally what I will do on engines that operate at extreme engine speeds is I'll take it down to about 40 thousandths or 45 at the most. And I will run the seat 5 to 8 thousandths bigger than the valve. There's a specific reason for this. Titanium valves only. Titanium on nitrous engines or power adder engines grow. If you look at the coefficient of expansion of a titanium valve, they don't even start to expand until they hit about 425. And then it's almost exponential to their peak by 475. So they just go boom. And wow. So on a power adder engine, you can run a 50 wide seat 10 thousandths bigger than the valve because the valve's going to grow 18 thousandths in diameter anyway. So But on a normally aspirated engine, I'll run it right out to the edge at 40, 45 for high engine speed stuff, because I know that thing's going to go 50 thousandths wide. It's going to beat 50 thousandths wide within the first 2 passes. And it's going to hold there. It's going to Brunel that surface harden that out to about 50 and hold there, at least I hope it does. And that's only if the wearability, the compatibility between those 2 metals is correct. Mm-hmm. Titanium wears with nothing. It is incompatible with every other metal. It will gall instantly, which is why coated valves are really, really awesome, because you just rerun them. You can do a valve job and just rerun them again. And they won't beat a seat out as much if they're designed properly.
But I thought beryllium seats could withstand that.
They can. And they have some embeddability, and they reduce valve bounce because they don't transfer the energy directly back into the valve.
They absorb it. They absorb the energy when that.
The energy goes into the head. Where an iron seat, or God forbid, a powdered metal seat, which is the worst seat in the world, period, bar none, will transfer all that energy back into the valve and just bounce that sucker right back off the seat. But alloy valve seats are much better for absorbing the shock loads of the valve. And there's another scenario as well. Oh, by the way, I run them 50 thousandths wide if I have to run an iron seat with a steel valve, because they won't beat out as much. And I will run them 40 thousandths narrow, 5 to 10 thousandths in on the valve diameter if I run a titanium on an iron, because they are going to wear the shit out of those valves. If you run a titanium valve on an iron seat, your valve wear goes up by a factor of 10.
Wow.
So if you got 1,000 runs out of a set of valves, you're lucky to get 100. And nobody puts that many runs. So if you got 100, you'll get 10 runs out of them before the margin's gone, and you can almost shave with them. They just destroy the valves. So running iron seats of titanium valves is not a good idea. But you can do it if you coat the valve. If you chromium nitrate the titanium valve, you can run them on cast iron seats. But I still don't ever do that if I can possibly help it. Some classes I can. So we run Tide. The other thing is the valve design itself will dictate how thin you can run that seat. The deformation of the valve, if you look, this is the valve head and the underline. When the valve hits the seat, it tulips. Okay? That valve will sit there and work on the seat. So that 45 degree, or let's say it's a 55 degree, when it strikes that seat, the valve deforms and the valve seat comes in. So it's sitting there constantly like an oil can.
Yeah.
So if you design that valve in such a way that it deforms at higher engine speeds, your seat wear will escalate as well. So you should also run on those. If I know I'm going to hit like 11,000 RPM and this thing is going to go out there and have to run 50 runs before I see it again, I'll go ahead and run a 45, about 5 thousandths in on the valve, and give it a little room to wear. And by the way, when you do a new valve job on a brand new set of heads, those seats are going to move. They're going to move. Yeah. And you're going to come back and those seats are going to be 55 wide. And then you do a valve job, and they're also, the seats also sink in the middle, by the way.
Yep.
Heat and expansion. The second valve job is always, 5 to 8 horsepower on the average. So anybody that gets a new set of cylinder heads, don't think they're going to seal up perfectly, because you're going to make 20 runs on there and you're going to have leak down between the valves a lot of times.
Nope.
But we have cylinder heads and seat combinations. Yeah. We don't put them in with a lot of press to instill stress in that area. So as it heat cycles, that stress makes everything move. So what I'll do is I'll put the seat rings in there with 6 on the intake and 8 on the exhaust, instead of 10 and 10. And what that does is it causes less stress in there. So as the center of that chamber heats up, And what happens is the center of the heats up and the valve seats go like this. So the valve's hitting on the center and wearing more right there on that center, and it cools down and now it leaks. But as the cylinder head seasons itself, after its expansion and contraction is over, after about the first or second valve job, it'll hold for a long time.
So when that valve's smacking against the seat, that seat's actually moving. It's taking the heat, it's taking the force, and it's actually moving. The head of the valve has got to also be moving. You can't have one without the other moving. It doesn't make scientific sense, right?
Yeah, and that
valve is going like this in some kind of fashion.
And 5/16, it's like we did 11/32, 5/16, 7 millimeter, 2 550 valves to 10,000 RPM. That was a really cool test.
Okay. And
it showed that the thicker, the more stability we put in the stem, the seats didn't wear as much. Go figure, right?
Yeah.
Of course. So the 7 millimeter would beat the shit out of them, and they'd go to like 65 thousandths wide because the valve would come up and then rattle back down the stem.
Oh, yeah.
So it was hitting off every time. So the length of that guide, and that's why the ProMod guides are like 3/750 long. You know, they're really super long guides.
Yeah, for that valve
stability.
You know? Yeah.
Well, and you run.
Okay. Love you. Bye. Give me a kiss. Good night.
Good night.
See, we've only been here an hour and we're just scratched.
We ran 7 millimeter stems to 10,000 RPM, and they showed a lack of over rev and a lack of peak in power because they weren't sealing up there, and they accelerated the seat and guide wears considerably. So what we did is we just stuck the valve guide way up next to the seat, and then I tapered the guide down, and that got rid of most of it, but it didn't get rid of all of it. So we went back to the 5/16 hollow stem for more support.
Manuel Ocasio, $4.99. Thank you for that. We appreciate that. You know, there's a couple other people I want to give a quick recognition while I'm finding the questions. Here's one for you. Savage Fabrication, thank you, $9.99. Most owners have diesels to tow their drag cars to the track. Are there any big things with them to keep in mind and watch for when it comes to low RPM dry flow system on large bore? Thank you.
I'm not going to comment on anything diesel.
All right. Sorry, Savage. We owe you that.
Not my forte. Sorry.
Sorry, brother. All right. Let's see what else we can come up with. Here's another one. Man, guys are really, this is great stuff. Rub Dub Falco, planning on a 13-to-1 compression ratio, 8,000 RPM NA motor using a C5.R block, All Pro LS7 LSW-1 heads, ported by Rich at West Coast Cylinder Heads. What intake manifold is recommended to support 800 horsepower to fit under a cowl hood C5 Corvette hood? I don't know about that, but
I would call BTR on that one.
Who's BTR?
Brian Tooley Racing.
There it is. Good question.
Or you can get a custom billet manifold done for it if you want to absorb that cost. And this is like one of those situations where it's needed.
Right.
Because there is no manifold that's perfect for what you're trying to do. So custom, the only way to optimize that situation.
And he's got a killer car. I mean, the thing sounds beautiful. So it's like I tell people, you know what? Pay once, cry once. It's always best to buy quality stuff if you can afford it. Bill Fiordi, straight line intake runner to head port through exhaust port and exhaust header with provisions for swirl, revision and scavenging. Straight line, always ideal.
On the intake tract, an absolute straight path is always ideal. Always. I mean, the ideal situation would be a runner aimed up with a constant taper all the way to the seat.
Yep.
And as a matter of fact, if you look at the new Corvette engine, that's exactly the way it is.
Really?
Yeah. It is a perfect constant taper all the way to that seat. And it is straight straight, straight. Anytime you want, and you look at manifolds and they have these arcs and they look pretty.
Yeah.
And in your head, you're thinking that air is just going to follow around that. No
way.
That air goes in a straight line regardless of how much you bend that runner.
That's true.
So what happens is on the inside of that bend, that's where the high velocity air is. On the outside of that bend, that's where all the fuel goes. There's no way to maintain a uniform airspeed in a bent runner. I hate it, hate it, hate it. And, there's a lot of manifolds being 3D printed now.
Yeah.
And CAD designed and 3D printed. And I'm going to get off on something right now. Somebody's going to kick my ass for this. Anyway.
No one's listening to us. Don't worry about it.
People design, there's a lot of manifolds that are being designed, and some people are making the same old mistakes that everybody's always made. And we don't say anything. And we don't say anything for a very specific reason. That's a feather in our cap.
Right.
Because we can charge the customer $2,500 for 25, 30 more horsepower, which is cheap. And if somebody else just drops that manifold on there, I thought there would be a day where I could stop sawing manifolds into 4 pieces and weld them all back together and remachine them, but that hasn't happened yet. It's decreased quite a bit, but the modifications to manifolds are something that, if you went and said, hey, Joe Blow, this manifold that you've designed, you need more runner separation. You've got a stall here. You've got fuel separation here. Your outer runners are starving. They're on the wrong harmonic. They're about 300 RPM off. If you told him all that, 90% of the time they won't pay attention to you anyway. So it's just like, why not give your customer that advantage and just save your breath?
I was at APD yesterday and I was looking at their intakes, and they have billet intakes that come in 2 halves. It's cool as hell, man, to see it, how they pour. It's amazing, man.
Yeah, those CID intakes are rather nice. Yeah, they're nice.
Let's see. AC, Cullen. Now, he's an old dirt tracker that used to race a Cleveland and a Cougar. How important are those same angles on the exhaust valve seat?
How important are those same angles on the exhaust valve seat? Not as critical. Not nearly as critical.
Okay.
The pressure recovery zone of an exhaust port is in the bowl past the valve. And it's a restricted area. So the valve is here on the combustion chamber wall. The idea with an exhaust port is to get the center dividers to lay them down so the air can come in to the valve and make both combustion chambers the same angle. Don't lay one back more than the other, and have an offset velocity airflow situation. This is your convergent area for an exhaust. So the air will come into the exhaust head and then split around it and then recover its pressure past the throat. And this is why tulipped valves, the valve angle, the back angle and radius are just so critical. Now, back when valve weight was not important on higher or on engines, we were only turning to 9200. I had a 30 to 31 degree back angle on there because the more back angle I put on the exhaust valve, the better the pressure recovery. The valve flowed smoother. It flowed more air across the board, and it was smooth, absolutely smooth.
Check that out.
Always made more torque. That always made more torque and held torque longer. But now as valve weight considerations have come into play, the higher the engine speeds we pushed, we've had to take that back angle down. And we've developed ports over the last decade around that fact. And yeah, that's a heavily tulipped valve. That is a tulipped valve. You can see as it opens that it controls the pressure drop past the seat. If you don't have that, again, you don't want to just open a valve and have it an open atmosphere. It's going to initiate turbulence. So if you have that back angle there, it recovers that pressure into the bowl at a uniform fashion, and it's smooth. It smooths all the air out. Now, on an exhaust port design is completely different criteria. Everything we look at on an intake port is not applicable to an exhaust port.
Yep.
What I look for on an exhaust port is how much area can I get that throat to? How big can I make it? Maintain stability and have that port smooth and move air at the same time. Getting those 4 things, which means more area, good pressure recovery, smooth flow. Let me say that again. Smooth flow and high flow it's probably one of the hardest things ever done, because it's on a high RPM engine. You need those throats out there at 94% of the valve, which you would never do that on an intake. You're dumping the pressure and you're also having to turn it. You don't want to. And if you'll look at all the high RPM cylinder heads, they don't turn the valve. They don't have a 90-degree exhaust flange. They have a 14 or an 18 or 20. The reason for that is to make the floor and the roof almost as equal distance as you can, so you don't instill a gradient and the air runs over itself. So if you just had a straight wall, the air on the roof and floor have the same velocity. If you bend it, the floor tries to speed up and the air tries to tumble by the time it gets past the apex of that bend. And it is an impossible situation to cure. If anybody plays with cylinder heads, put it on the flow bench and you'll feel with your finger on the flow bench there's a hole on the floor. There's no flow there. That's where the flow is actually exiting, turning around, and coming back in. It's actually sitting there on the floor doing this number. And when you have that situation, all the flow on the roof and none on the floor, that takes the whole engine's power band and narrows it. It'll come on the cam later and it'll leave earlier, because the reversion in the system, when the exhaust goes out of tune, it acts on the lowest airspeed area. So if the floor is dead, that pulse will go right into the combustion chamber, right on the floor. But if you can get that exit velocity fast enough, and what is fast enough? It's 300 to 310 feet per second exit velocity. If you can get it to that point and get no more than about 30% gradient from top to bottom, you won't have that problem. It'll come on the cam sooner and it'll leave later. That power band will. Right. There's other ways to do this. If you have an exhaust exit and a header, by the way, the header should always be bigger than the port. Some instances you can't do that with low RPM stuff. They're almost matched. But if you have a big one, the header's bigger, you match the roof and mismatch the floor. So what happens is the air, that slow air where the pulse is going to act on, comes off the floor and forms a vortice right down here at the bottom. That's low pressure, low pressure. So when that high pressure pulse comes in to act on that port, that low pressure vortex cuts it right down, and very little goes back into the port. It will half the amplitude of that going into the combustion chamber. So it comes on the cam earlier and leaves even later. Now that's a Band-Aid situation. It's an anti-reversion deal. And on the pro stock stuff, what I used to do is a lot of times if I had a really good even velocity, I would match that big header up to the top and bottom evenly, and then put ditch cut all the way around the port back in with a mill. So inside
of the port.
Yeah, into the cylinder head. Yeah. So that would be like 1/4 inch deep all the way around. So what it would do is the exit velocity would form that low pressure vortex 360 degrees all the way around the port. So when the high pressure tried to act on it, boom, cut it down. So it would come on the cam sooner and leave later. There's a whole bunch of ways to do that. If you can't mismatch the header, you can just flare it right at the exit there.
What size primaries are they using? Were they using like 3-inch or something? How big are they?
The Pro Mods will use a 3+. Okay. I mean, the exit on the exhaust port on a Pro Mod's 3 inches. I mean, that's the exit on an exhaust port. So, I mean,
Okay.
yeah, 2875, 2 3/4. Now, an exhaust pulse, the system tunes up with the harmonics and everything. The exhaust is only 800 RPM wide, where the intake can be 2000 RPM wide, the tuning there.
Yep.
So what do you do with a high RPM engine? If you'll notice, the headers are really short, really, really, really short. Short little stubby collectors, merge collectors.
28 or something,
What you do on a high RPM NA engine is when the power band noses over, that's where the exhaust starts pulling. You tune the exhaust past peak power. Okay. So you're using the intake track tuning up to peak power, and then past that, the exhaust tuning comes in and starts pulling air through the motor to help
scavenging, you're saying, right?
Yeah. It helps the scavenging so the power doesn't nose over and carries out further.
Which you can achieve with like a step header. That's where our step header will come into play, where it'll be smaller, right? So it'll keep that velocity up, and then it goes into a bigger,
A step header does two things.
Yeah.
You're referring to pressure recovery there.
Yep.
That is pressure recovery, because as the hot gas moves through that header, it is cooling down and expanding and taking up more space. So in order to maintain the same airspeed, the pipe has to get bigger and bigger and bigger.
Okay.
So if you maintain the same header diameter and it's cooling down, the air is seeing a higher and higher pressure because it's seeing more and more resistance. That is a pressure recovery dynamic. And if you look at Formula One headers, they're a perfect taper. Perfect taper.
Never seen them. Let's see here. This is a good one here. Wow. I like this. What's a good start for cutback margins?
Twice the width of the seat. So if you have a 45 or 50 seat, you make the seat and back cuts twice as wide.
There it is.
It'll tune right up. It'll tune right up.
We'll have to make that into a YouTube short.
And then, if you want a little more top end flow, you make it a little wider back cut. And thin, so you make the back cut 10 thousandths wider than the seat cut. And what that will do is throw about 5 CFM up top. Or if you want to shear it really hard and help the low lift, you run the seat cut about 5 to 8 or maybe 10 thousandths wider than the back cut. And that'll have more shear, and it'll help tune up and stabilize the low lift portion of the flow curve.
There you go, Grom Racing. Take it to the bank.
And that is just a tuning variable that you do for anything. And I could go at Rares. I had over 100 valves on the shelf with different varying back cut widths and seat cut widths.
Yeah.
And I could just, on the flow bench, I could just grab them and throw them in there real quick and see the trend and say, okay, well, this needs this.
That's nice. Already done, Hans Bloom. Is there a relationship between intake valve size and how far away from the bore wall? I went from a 34 millimeter to 30 millimeter valve on a 57 millimeter bore. So now it sits pretty far from the bore. Vintage Honda Hemi road race.
Okay. Once you get, and I'm going to look at a normally aspirated high RPM engine, we shoot for 200 off the bore wall because we know that the valve will almost see itself as unshrouded at that point, if that makes sense.
Yeah.
At 300, it doesn't even see the bore wall at all. What you have done or should have done or seen is when you went to the smaller bore, you went to a smaller area, but you also increased efficiency by having it further off the bore wall. What you should see is less shrouding and turbulence and increased efficiency of the system. It should have automatically picked up efficiency. That's not to mean flow, but it will become more efficient. It will flow more per unit area if you do that. And that is always a point of contention, of course, because you have a 400 cubic inch motor, you need a 250 valve or 325 valve in a smaller bore, and you need it 200 off the bore wall. Well, that pretty much sets your exhaust size.
Yep. Thanks, Hans. Michael Schmidt, 1350. Thank you. Great.
Oh, by the way, could you go back to that question?
Yep. Now I got to find it here. Let's see. You guys talk amongst yourselves. So, you know what? That's a good thing that you brought up now. I don't know if I can find it right now quick. That you brought up, Darin, about doing this, about having a section on this channel where we can have this kind of discussion, maybe an hour here or there, or have questions funneled just to you. So I think that could work quite well. So I think that'll be fun. Just have to figure out how we're going to do it. And sorry, guys, can't find it. I don't know where the hell it went.
Thanks, Michael Schmidt.
Yep, I appreciate it. Now I got to get back in the game.
The reason I wanted you to go back is I thought as soon as you took that down, I thought he said it was a Hemi. And if it was a Hemi, what I said isn't exactly. I remember
seeing that part of that. Let me go back.
Okay, well, let's back up a minute. If it's a Hemi, what I just said is not true. Because a Hemi can run the valve right on the bore wall and maintain ungodly efficiency numbers. And it's actually advantageous to do this. Because you have a bore wall sitting here, you have a valve here, okay, whatever angle that valve is, and the short side is just a continuation of the bore wall. So if you move the valve off the bore wall, the air turns back into the bore wall, initiates turbulence, and valve efficiency drops on a Hemi.
It said vintage Honda Hemi road race. I don't know what that means.
If it's a Hemi, you can run. The only thing holding you back from valve size is clipping. That's the only thing holding you back. Now, I will say this. In some Hemi combustion chambers, it's easy to put too big of a valve in the dang thing, have too much area and too much flow for the RPM range that you're running. So if you email me at darinmorgan7854@gmail.com and give me all the specs, I'll tell you whether that's advantageous or not.
He said this is a 2-valve motorcycle, 11,000 RPM.
Yeah, you can't. The valve size is dictated by the clip and almost nothing else at that point. I mean,
go as big as you want. Don't break the valve.
Yeah, because if it's a 4-valve, you go as big as you want, and then you control the average airspeed with the port and everything else. But if it's a 2-valve, you're probably not going to go. You're probably not going to get into a trouble going with a bigger valve as opposed to a smaller one. Now, on a wedge or a cannon valve, 2-valve deal, you can get into trouble going with too big a valve. And by shrinking the valve, you can increase the efficiency, low-end torque numbers, mid-range, and everything else, depending on what RPM range you're operating. It's engine-specific, again, RPM-specific, again. But, yeah.
Terry Grover, hey, Tim, you get a lot of opinions from headquarters, but with Darin Morgan, you get facts. That's a fact, Jack. Thank you very much. Let's see. Ed Machine. Can the valve seat area and angles leading into the seats and away from the seat be considered an orifice, regulating the flow through the port, affecting the discharge coefficient and the Reynolds number?
Absolutely, verbatim.
There it is, Ed. You got it. That's it.
Yeah, the whole system, the Venturi section that I'm referring to is 1 inch below that seat, starts at the apex of the short turn itself and the end of that combustion chamber. That is the Venturi section. That governs so much of the power. It governs how the engine can accelerate, how much power and torque it's going to make, what the power band's going to. It governs so much because that everything else above that is just airspeed and taper. That's management. That's easy. But turning the air around that valve efficiently at all lifts, that's the hard part.
There you go, Ed's Machine. So make sure you guys check out his channel. He's got a lot of stuff going on. The hobby, I haven't heard from you in a while. THC Racing. Look what I stumbled across. I'm on my way back to the hotel. Down here in the Carolinas doing recovery work. This is awesome surprise. You bet it is. You know, one year, 11 months, and 9 days. So who's counting? Grom Racing again. When calculating cross-sectional area for a dry port with direct injection, is there considerations taken versus when calculating it for a wet port?
Absolutely. Absolutely. And again, this is engine specific because now I know what you're looking for. You're looking for like a simple ratio. It needs to be 10% or 20% smaller, or the valve needs. I don't have the experience necessary with dry flow systems to give you hard numbers. Generally, across the board, you need less valve area on a dry flow system. You need the same airspeed characteristics in the system that you need with a wet flow system. It's just everything is smaller. And you can also get away with some really radical turns on low RPM engines. Like if you look at the Godzilla cylinder heads, perfect example of what I'm talking about. That port comes in, makes a freaking hard turn. It's got a high, I mean, the short side's built up and just turns immediately. It's what we call a hypercritical short turn. That short turn is designed in such a way that it will give the engine the required airflow that it needs to make the power that is required, which is not a lot.
Right.
But what it does is it instills mixture motion at lower engine speeds, because those engines spend 98% of their lifetime at 1,500 to 2,100 RPM, cruising down the highway. So you need airspeed at the short side spiked and a huge velocity gradient from side to side to initiate the swirl into the combustion chamber. And that's what they do. The LS7 is the same way. They did the same thing, just not as drastically. They didn't instill the swirl, the mixture motion. The short side on an LS7 is real steep. I mean, it's almost straight up and down. Well, that hypercritical short turn is what pulls the fuel. When you hit the throttle, that's the high velocity area. That's where the pressure drops and all the air moves to that point because it has a big valve. And the Godzilla is the same way. It's got good valve area, plenty of valve area, a little bit more than it needs. So it has no airspeed in the system. So when you hit the throttle, you got nothing. So you spike that airspeed at the short turn, you initiate the swirl, the mixture motion. So now you have a low pressure area to move the air into the cylinder, and you have mixture motion. So at 1,500 RPM, when your VE is real low and there's not a lot of air in there, it's still mixing the fuel. So it burns good. EPA efficiency down there is awesome with those engines.
You want to know what Warren Johnson told me the other day? I was talking to him on the phone, and it's funny that you said this because I never even thought about this that much. But I said, Warren, I go, what do you think? What's more important to you, velocity or flow, airflow? What do you think about that? I mean, this is what he said to me. He said, you know what? That doesn't matter to me at all. I don't care about that. What matters is the mixture. It has to have a certain degree of swirl and tumble. Those molecules need to have that movement, that motion. What I care about in a pro stock engine is efficiency and atomization. You know, homogenation of the fuel is what he told me. He said, that is what makes power. And that is what I care about. I don't care what those runners look like or the air that's going through them. I want this mixture to do this, this, and this. That's the secret. So he told me that, and I'm like, what does that sound good? Does that sound right?
And I understand totally what he's saying.
Yep.
it's kind of like when people say flow benches don't matter.
Yeah.
It doesn't matter to the actual power that engine's going to make.
Yep.
Because the best flowing cylinder heads almost never make the most power. Sorry to tell you.
Just numbers. I get it.
Yeah. Sometimes you have to increase the airspeed or twist the short turn or do this or do that to make it function on the running engine. And that's where R&D comes in. You have to realize that people wonder, how the hell can you get 1,500 horsepower at 499.8 inches NA? It's because we've been working on everybody's been working on the same engine for 40 years.
Yeah.
If all you had to do was go in the shop and work on that one engine every day and nitpick every single tiny little freaking variable, yeah, you're going to optimize the situation. It doesn't matter what it is. It doesn't matter if it's flathead. If you spent your life doing that, you'd be the most powerful flathead builder in the world.
Yeah, you would.
Yeah. So, yeah, I understand what he's saying.
Okay.
I mean, granted, you have to have a certain amount of airspeed. You have to have a certain amount of flow. But having a homogeneous air-fuel mixture entering the combustion chamber, when that spark plug ignites,
you want all that fuel burning.
You can run more compression. Yep. You can run more timing. You can run a whole bunch of things that you couldn't do if it was not homogeneous. If it had a lean spike somewhere in that combustion chamber, you're going to get into trace detonation earlier. So you can't make as much power. Yeah.
It's like you sit on the phone and talk like this. I talk with him like this. And it's funny because you can explain it right down so I can understand it. He can do the same thing. And he said, one thing I can tell you about Morgan is he ain't a bench jockey. That boy's a thinker. And that's what we need is thinkers. That's what he said.
The thing is the flow bench is simply a tool. It's a rudimentary static flow testing instrument. And all you can do with that thing is gain insight into what is actually going on in the engine. It won't tell you whether you're going to make power. It won't tell you whether what you've done is right, because there's more than one way to skin a cat. Yeah, if you look at faults, you look at all the pro headquarters out here, we all do it a little differently.
Sure.
But our air speeds are the same. Our tapers are probably the same. Our runner lengths are the same. Our discharge coefficients are the same. Our valve sizes are pretty much the same. Everything's the same. But where we put it in the combustion chamber and how we treat the air-fuel mixture entering the combustion chamber, trying to make it, like Warren said, as homogeneous as possible, that's where all the R&D comes in. I can't count how many times Larry or somebody would go to lunch and I would stay behind and yank the heads off. They'd yank the heads off before they went to lunch because I would want to put epoxy somewhere and try something. Just try something. Try a wing over here. This chamber is burning like shit on the intake side over here. How do I get fuel over here? I had a scenario, and sometimes you got to think, and I don't like using the word out of the box because you have to know how to think in the box before you think out of the box.
Straight common sense.
It's like, okay, I have a problem. What change can I make to fix that problem? So we had a cylinder head, and I'm not going to say customer or type of cylinder head, but it was lean on the intake side, and it was detonation prone in the combustion chamber, and we needed fuel over there. It had to get, how do I get fuel over there? It had an offset port, a huge velocity gradient. All the fuel wanted to go to bore center, and it leaned out the intake side. So I thought, well, there's wet fuel on the floor, which is why I put a wing in there to spike the fuel up into the airstream again. Why not use that fuel and put it over there? And I thought, well, how the frick am I going to do that? So we took a hacksaw blade and sawed a frickin' groove into the floor right over to there. So all the wet flow went into the groove and went over there, and the detonation went away.
Really?
But it's crude as hell. And if anybody sees it, they're going to go, what the was he thinking? But it fixed the problem. You could add a degree of timing. It made 10 more horsepower on the average, and it was fixed.
Do you believe you can't, air does not turn corners. You can't make it turn a corner. You can only influence a direction.
Influence lightly, ever so slightly. And when you have to turn air, that changes everything. because now you're dealing with multiple dynamic effects. The Coanda effect of a short side. Everybody go to Google and look up Coanda effect, Coanda, Coanda effect.
Got it.
And you can demonstrate it in the shop. Okay. You can take an air gun. Okay.
Yep, blower.
Just lay it on the table
Mm-hmm.
right next to the edge, and that high velocity air will turn that corner. As a matter of fact, you can take any port and take an air gun and lay it on the floor, and the air will go right around the corner.
I'll have to try. Okay.
When you research Coanda effect, it'll all make sense. But basically what you're doing is you're lowering the pressure at that apex. As the airspeed increases, the pressure drops. And if the pressure drops, the high pressure air pushes down on it. And it forces it around the corner.
Yeah.
It's an amazing effect. And we have to balance that effect with the gradient from roof to floor. You want it even. You would like it even. You can't get it even. You get it as even as you can. But that Coanda effect, the lowering of that pressure at the apex of that turn, especially on low speed engines, is what pulls the fuel around the corner. Let me say that again. The lowering of the pressure at the apex of the short turn is what pulls the fuel around the corner, because particle flow and molecular flow are two different things. And you can look it up on Google too. If you look up airflow and particle flow, there's a lot of testing you can see. So this fuel droplet that is microscopically small has a hell of a lot more mass than the air blowing through it, trying to carry it in. The air blowing past that fuel droplet is what carries it into the combustion chamber. So the air is moving faster than the droplets are. Soon as that pressure drops, it pulls that fuel droplet around the short turn. Without that pressure drop, the fuel won't turn. The fuel slams into the back of the bowl, deatomizes, and kills the homogeneous air-fuel mixture in the combustion chamber.
Does scavenging have an effect on that? That's going to have to pull. It's not going to pull, because where are we in the?
It'll always, that's a secondary tuning.
Okay. Okay.
Yeah.
Where are we in regards to overlap right here when we're talking?
That's on the beginning of the inlet stroke.
Okay.
Through the entire lift curve, really. And the short side doesn't become the apex of that turn, wherever it's at, does not become reactive until what's called, and I coined the term back in the 90s, a Venturi convergence point, because that's what it is. It's where the throat of the port equals the curtain area. So the throat area is 4 inches. So if you lift the valve the 550 thousandths lift, now you've exposed the curtain area at 4 inches. So now both areas are the same. At that point is where, if the port is screwed up design-wise, it's going to go turbulent instantaneously at that point. That's the point you have to really consider and look at. Past that point, the short side airspeed becomes reactive and starts pulling the fuel.
Because I remember you saying something about the short side. If you raise the short side, it changes where the RPM's coming in, right? You lower the short side. I always remember you said, Tim, don't mess with the short side. You're going to wreck that head.
And, so many people in this industry, so many of the head porters call themselves short side gurus, because amongst us, because that's the most finite, other than the throat itself, tuning that. I mean, it's a simple proposition. If it's straight up and down, it's going to make power at 1,000 RPM, and then 2, and then 3, 4, 10, 11,000. The more you lay that back, the more straight shot you have, the higher the RPM potential gets. But you wouldn't want to use a laid back port for a low RPM engine or a stood up port. And there are cylinder heads out there like spread port cylinder heads. There are certain cylinder heads out there. And again, there's more than one way to skin a cat. And I'm going to get back. I'm going to take a little break, get something to drink.
Yeah, I'll keep talking because believe me, I can talk. So yeah, 124 people here. So I appreciate you guys being here. I could tell you there's a whole list of people down here, and it's hard for me to go back and forth and try to keep it going. I will tell you this. It's only been an hour, 44 minutes. So if we stay 3 hours or what, I'll get to your messages, everybody, and try to cover all this stuff. So please stay in tune. Let me run down here and see what we can find out here. You know, I appreciate it. J Jones MX, $20. Thank you. You know, like I said, any of this, the money that you're donating by Snapchat, not Snapchat, live chat, it's going right to Darin because he's taking the time here from his family, you know, to give us this information. You just don't learn this. I mean, I am like, when I sit here and look, I'm not talking because I'm trying to absorb this. And I will put this on in my garage when here, DBG, and I will replay this with the speakers going because I don't need to see who we are. And listen, because every time I listen to one of his our live chats, I always get something new out. And in fact, I was dissecting them into like little appetizers where I could take tidbits like this and make them into shorts and try to put it together. There's a lot of extraneous talk that we have. We know we all like to talk, especially me. So I'd like to cut it down so that you guys can enjoy it without that. And I saw that someone else had mentioned, it said, yes, I would like it for you to have a little section on your YouTube channel where Darin could be, and we could all meet on it. Let's say a Friday night, we're going to have an hour of talking about whatever, only valve size or whatever, you know. I think that can work out. I'm going to plan that out if you guys enjoy it as much as I do. I also have a website. It's Cleveland Forever 351 Cleveland.net. That's my website now. I took it over from Todd Fuchs, so I can start moving things from YouTube to my website where I can have the merch. You can get that. We're going to have a lot of, maybe even have an area there where Darin will be. But we're going to expand this. Him and I have been talking about this. We got a lot of stuff going on, and we want to bring you guys here with us. So I appreciate that. Hey, Mrs. DragBoss, thank you. Hi, Mrs. DragBoss and Darin. That's great information, Mrs. DragBoss and the Bossettes. Thank you, my wife. It's my beautiful wife checking in. So thank you.
Going back. I'm sorry.
So I'm just kind of cleaning house there, Darin, looking through the messages so I can keep us posted and on time. J Jones MX donated $20. So I wanted to give him a big shout out. Thank you for that. We appreciate it. Let's get back to where we are.
Back to the Coanda effect.
Yeah.
Lowering the pressure at the apex of the short turn. You know, we're sitting here about wanting to not instill a gradient, a difference in velocity into the system, but that's exactly what the Coanda effect does. It lowers the pressure at that apex, which is what you want if you have to turn. But it can also be extremely detrimental, and the flow bench will not tell you. There are spread port heads out there right now that you will flow the same amount of air. They'll all flow 540 CFM. And these are 4840 bore space heads. There are certain ones that what they have done is they have a very abrupt short turn. So they spike the airspeed at the short turn something horrendously. And people want to know how fast is too fast. If you exceed your test pressure on the bench at the apex, the average airspeed across that, if you exceed your test pressure,
like 28 or something, right?
Yeah, 28 inches is 350 feet per second. Okay. If the average airspeed across that apex exceeds 350 feet per second, you're playing fire. Okay? Because once it hits 400, there's nothing you can do. That thing is going to nose over at 7,000 RPM no matter what you do, no matter how big you make the port, no matter how big you do. It doesn't matter what you do, it's over. Because that becomes a localized velocity choke at that point on the running engine. When it hits 150 inches at 76 degrees after TDC, that area is going to go critical and choke the port off.
Okay.
So what they do on the flow bench, and this is very easy, and David Vizard pointed this out back in the 90s, that you can have a short side like that, and you can have a huge bowl, okay, and it will recover the pressure and go out the valve. So what happens is when you have a hypercritical short turn on something like that and you're playing on the bench, you have to make the bowl bigger and bigger and bigger and bigger, and pretty soon it just starts flowing more and more air. Now you've got this huge bowl area over the short turn to slow the average airspeed down enough so it will move air on the flow bench, but dynamically on the running engine, it's a disaster.
I love this, man. I really do. Let's see what Bill said. I'm a Hemi canted valve and inline valve builder. Why do you think the trend has been seemingly inferior inline, i.e. Chevy, LS Series, Ford Godzilla? I mean, are you just saying because, Bill, is he saying because, there's advantage having canted valve versus inline?
Why do you think the trend has been seemingly inferior inline? In other words,
no one really cares about inline anymore. Everyone's going.
Are you talking about an inline engine as far as an inline six? Or are you talking about inline as far as
he's saying Chevy
or? Oh no, you're handed Cami inline.
An inline valve, yeah.
I.e. Chevy LS Series, Ford Godzilla, etc. I'm not under. Please clarify that.
Because I'm kind of lost too.
Elaborate on that question, please.
I was wondering if he was saying, why are people not going with the inline valve heads anymore and want to move everything to canted?
Because of the camshaft and valve trains. To answer your question, because of the valve trains and the camshafts available, engine speed is easily obtained.
Okay.
So, yeah.
Don Dotter, porting mods on the small block Chevy single plane intake on the 5 and 7 runners for the factory firing order.
Well, there's a class called stock appearing.
Yep. Fast.
I mean, you're talking about a big block Chevy engine that looks bone stock, that's making 965 horse through a dual plane intake method.
What? Is that Corvette?
Yep.
The one I'm thinking of? Yeah. That guy's serious, man.
Let's just say that stock appearing means just that.
Yeah. You don't know what's underneath.
There is an amazing amount of ways you can saw up an intake manifold. And there's nothing you can do with a single plane that's going to make it perform better just by porting, unless you redesign the whole thing. It's kind of like a set pat system, and it's going to sign off. If you just make it bigger, it's just still going to sign off basically at the same RPM range. It's going to make more power through the power range usually, but all the bends and the harmonics in the system are set with that design. So it's going to sign off regardless, because a dual plane has the runners from one port to the other connected. So as this companion cylinder is dead, this port is drawing on that runner. Well, it sees that whole length back and forth. So you have two runners, two ports using one runner harmonically. So what happens is there's no way to gain engine speed with that. It's going to sign off because you're going to run out of volume real quick. So if you make it bigger, you can make a little more power and get a little more air in there. But harmonically, it's a disaster, and there's nothing you can really do. The only thing you can do is saw out the divider and get in there and try and make the thing flare, get some taper in the system. And that's almost impossible too. Normally what I will do on a single plane is saw out windows all over the place. And those windows I will grind out, weld back in, and then you'll never know I touched it later. Right. It is stock appearing. And I port through windows. And well, I shouldn't say I do.
No, I do.
Jim at BES is the guy who does all those single plane manifolds, and he's masterful at it.
Is he?
Yeah. And he works for days on those things.
There you go, Don. Thanks for the question. So I had asked about if you and I do our own little, private type episode or however we're going to work it. And people said, yes, please. Riley Jones, Graham Racing. Yes, Darin, do it, please. The Shed, Greg from Australia. Yes, I'd watch the videos. Chris Williams. Yes. How about this one? Hope you can have Darin with Larry Widmer. So that's always a possibility. I was going to have Larry on by himself. I'd talk to him, but he said he would like to do it. He's just not ready right now. So I said, all right, we'll find out. He's got a lot of stuff going on. Let's see. THC Racing. Darin, do you need help? Any help filming? I'm in Indiana also, and I'm down at Tin Soldiers 2 times a month, whatever that means. Okay.
Yeah, I would definitely like to talk to you.
There it is.
I have problems starting this off. I tried to do it with a black backdrop. I tried to do it with the screens, the
green
LCD,
screen,
the monitors, TVs that you can draw on and all that. I was thinking
yeah.
I don't know where to start. So yeah, I need your input.
There it is. Let's keep going. Let's see. Greg the Shed. In another video, Baron was touched on about how much material. I think you meant Darin was touched on about how material thickness affects manifold performance. Can you elaborate? I think you're talking about different material, metal, aluminum versus cast iron versus phenolic or whatever the plastic stuff takes.
Different thicknesses and alloys have different resonant frequencies. They vibrate or they dampen in certain areas. Like I think it's 5245. I forget the exact alloy that I use on the plenum. I'd have to look it up. But it's a very soft, malleable, bendable alloy that is just like bubble gum almost when you're bending the dang stuff. And that's what I want. Actually, it's so soft that you hit it, it just clunks. It's not like 6061.
Ding. Yeah.
I want it to move because when I'm welding all that stuff up, I want all the deformation to happen, and not cause the flanges to move out. But as far as the thickness of the metal, the danger lies in going too thin or way too thick.
Mm-hmm.
If you're down under an 1/8 inch, it's really easy in the plenum area. It's really easy to have some problems. If you're under a 1/4 inch on the top plate, it's easy to get into problems. The runners themselves, I like to see them 180, 200 thick. 125 would be the absolute minimum. If for some reason, I don't know why, don't ask me.
Yep.
But when I make the plenums themselves out of like a 1/2 inch plate and then mill it down to like 350 or so, and I make it thicker, those engines don't ever seem to perform as well. And I don't know why. But the most danger lays in making stuff too thin. Okay. That's where. And what happens is you have 2 problems. It's if you have carburetors, you have the vibrations going up into the float bowls and everything. And depending on the height of the manifold and the frequency of the manifold, and that engine's shaking back and forth. Well, it's also shaking those bowls back and forth. NASCAR in the day had a hard problem with what they called foaming the bowls. The bowl would hit a certain frequency where the fuel would just turn to foam, lean the engine out. So we don't have those problems really today as much because the fuels are a lot better, mainly.
Jack. Hi, Tim. Hi, Jack. What's Darin's thoughts on raising port and putting a radius on port or chamber on entry of port? I put small trench in quench pad helps, especially with CE piece.
Okay. I think you're referring to what we call donuts. So you have a runner coming up, and it's on a flat plenum plate.
Yep.
And what we'll do is we will continue that radius into the plenum and back down to the plenum. So you have a raised section going into the plenum. I think that's what you're referring to.
Coming into the plenum, you're saying.
Yeah. So
in
other words, if you had a runner sticking out here and you built the plenum around that and just left the runner sticking in there.
Yep.
Yeah. That is very powerful tuning. What that does is it gives us the one thing that we're looking for as far as runner isolation comes into play. When you isolate a runner away from the other runners, and we're not going to get into that, but if you isolate the runners, the other frequencies and things that are happening in the plenum don't react on that runner as hard, especially in the lower RPM ranges. So what you'll see is increased torque and mid-range power. And sometimes, depending on the system, you can actually hurt top-end power by doing that. But it is a very powerful, I mean, you're talking 10 foot-pounds of torque. In a bad situation where you don't have runner isolation and you put those donuts, and I'll actually take epoxy and just slap it on there, mill it flat, and then hand grind it, and then grind the radiuses around it. So you have a raised radius in the plenum, at least a half inch all the way around. So it's perfect runner isolation, which is one of the problems with the single plane manifolds that are coming out. They don't have any runner isolation on the end runners, which causes them to what we call split harmonic. You have a power band in the center runners from, let's say, 6,500 to 8,500, and the outers are from 5,800 to 7,200. So you have a split harmonic, because what they do is instead of isolating that wall run, they continue it right up, which makes that runner think it's longer. So when you have runner isolation, it's very powerful, and what it can do is it can increase the charge density in the lower RPMs and the mid ranges. And sometimes you can get away, and sometimes, what I mean, only a lot of times when you have Hemis and they're pointed down at each other. By the way, when you do this with a manifold, the top end power goes down the tubes. The more you aim those runners at each other, the more power you're going to make.
All right, so let me get this straight. Let's do a couple things. The longer the runner of the tunnel ram, the power band is going to be where?
Let's say, look at the old tunnel ram, the Ford tunnel rams. What did
Yep.
they do? They went like this, didn't they?
Yeah.
They aimed right at the booster. Okay. Those things had god-awful reversion, because every bit of that force is just acts right on the booster. Well, what if you could take that force and transfer it back and forth?
You wouldn't be drawn on that booster.
The energy wouldn't be wasted, would it?
Yeah.
We learned a long time ago in pro stock manifold designs, and I don't hear anybody has ever talked about it, by leaning those runners down and getting them into a situation. Actually, if the port roof is like this, we never did this. This is a disaster.
Oh, yeah. I mean, look at that.
Leaned it down 2 degrees. And the floor would be like 4, and the manifold comes off of it like this. And I didn't know why it did this, because back in, I think it was 98, 99, I was just really perplexed at this, because you would think if you aim the runners up, it's a straighter shot.
Right.
The window area, everything looks better.
Yeah.
But it's a freaking disaster. And I just couldn't make sense of that. And then Carl Foltz one time says, well, it's taken load off the short side. Maybe that's one of the reasons. And I thought, maybe that is one of the reasons. Now, you got to remember, all of us head guys out here, we still speculate about a lot of this stuff.
Sure.
You know, so what happens is the apex of the short turn has the lowest pressure, highest velocity of anywhere else in the system, period, bar none. So if the short side's down here and you aim this sucker up, you're loading the short side harder. So if you bend it down, you have another short side that takes the load off of this one. It drops the pressure a little here before it gets to here. So your short side airspeed apex is a little lower.
Slows down.
That makes sense. And the other thing, the other speculation or theory that we have is instead of wasting that energy up at the booster, you're actually displacing it back and forth. Maybe that crosstalk actually helps. I see this still today in a lot of people's manifolds. They try to aim them up. In some cases, in lower RPM ranges, when you have to have a long rudder, you don't have any choice. You've got to do that. I mean, it's functional. It's just, you have to do it. But in low RPM range, our engines, these suckers are aimed right across each other.
You want to know what you could do that may help? Put the discharge nozzles of the accelerator pump under the throttle blades.
I knew you were going to talk about that.
That's what I would do. You know, who says they have to be at the top of the carburetor, right? Why can't you put them below the throttle blade?
You were talking about an individual who has somewhat perfected that.
Well, it's still under development. But I will tell you guys this, because it's kind of, there's so many questions. We'll just keep going, but it kind of brings in something that's new technology, and I'm making a video on it tomorrow. But just think, if you could put the discharge nozzles for the shooters underneath the throttle blades, how that would change things. You wouldn't have pullover. You could control pullover. There's a lot of things. You could use half the fuel that you would need for the pump shot up top because it's going less distance. So that's going to change air fuel mix.
That's a great idea. And I would love to talk with this individual at length of how he is controlling
check valve
with the variable pressure drop underneath that throttle blade. That is quite a task. But I will say that I can't count how many times that I've been, you know, you go in the dyno room and you have a flashlight and you're standing over the Pro Stock engine and you're looking at the carburetors during a pull.
Yep.
And you can see which booster is offset, which booster is flowing more, which you can visually see it. And you can also see the pump shots freaking pulling fuel on one barrel really, really bad. So that's how we used to have to do it before we had cameras, is actually ride the engine and look down the barrels. And what's funny about that, and this is during the days when we were like 95, 9600 RPM. But your eyeballs at certain frequencies throughout the power range would vibrate so much it would completely blur your vision out, and then they'd come back. So between like 88 and 9,000 RPM, my eyeballs would just blur out and then come back again, just from the harmonics coming off of the carbs.
Amazing stuff. And by the way, I'll just give you guys the insight because I work with APD. I've been doing videos for them, so I'll let the cat out of the bag. No one's listening anyways. 128 or 130 people, but they have this carburetor, and it's in developmental stages. So you can't make any promises, but it does change things a little bit in regards to that. So I liked what George said here. So George says definitely on episodes on math, more episodes on math. How about Darin doing a book even? Maybe something along the lines of Billy Goldbold's High Performance Cams and Valve Trains. So that's always a possibility, right, Darin, a book?
I've already been approached about doing that book. And I don't think that's going to happen. Because
really? You think so?
I didn't want to do it.
Maybe you don't have to do it.
And here's the reason why.
Okay.
Billy Godbolt did an unbelievably good job of taking extremely complex subject matter. And he did an unbelievable job of boiling down all that into a clear, concise, understandable, technical treatise. Okay.
Yep. Treatise. Yeah.
I am incapable of that. It's going to take me 20, 30 hours to explain this. And you can't put that in a book. You can't put it in a book.
Nope, I get it. But we can talk about it and record sections of it. And that's the key right there.
I mean, I could put the basics in a book, but what good is that going to do?
Don't you want to see us talking? That's what makes it fun to listen to these topics is interaction. We do little short videos or however we decide to do it. I'm telling you, it will go crazy. People will be here because this is the stuff this is what gives you the advantage over the other guy with a winning combination. It's the little things that count. And you may not ever port heads. I'll tell you, I got it. Like I said, I talked about APD. I got an offer yesterday. They have a 1020 flow bench. They said it's mine. I can do what I want. I'm going to do my first set of heads. Darin and I already talked about it and see what I can do and see if nobody can figure out how to use a flow bench and do some work because I find it fascinating, and you, with your experience of whatever, 30 years, I don't even know how many years, tell you the
40.
truth. 40. Okay. Yep. 40 years of doing this stuff and being able to explain and answer questions on the spot. I mean, that right there it's amazing. And I think that's what guys like to see, to ask a question about valve size and you just, yep, there it is,
me and Joel DeBose and a couple of other people in the industry, we're talking, and what I do for a living is kind of a dying breed.
This whole industry is dying. We kind of go to that part, the left is whatever it is. I don't know who it is, and I'm not going to call names. I just know that it's trying to get shut down. They want control, and they're going to control us by controlling the materials that we use to make our products to do what we want to do. And that's what it comes down to, the raw materials.
And now I get to get up on my soapbox.
All right, hop on there because I'm thirsty.
These venture capitalists are fucking destroying our sport. They are destroying it.
Yep.
They've bought all these companies, stripped the shit out of them, killed all the R&D, fired all the R&D guys that knew anything, concentrated on only the products that make the most profit so they can build that company up and sell it later.
Yep.
That's it. It's over.
What's
going to happen in the next 10, 20 years is we're going to say, screw the aftermarket. We're going to build everything ourselves. All these engines are going to be billet. They're all going to be in-house. There's going to be engine combinations because we can do it. We're doing it now.
Yeah.
I mean, we've been doing it for over a decade. 5.3, 5.6 bore space engines. I mean, anything we want. I mean, the CNC industry it's a whole cottage industry. We have people out here who can do anything you want. It just drives the cost up some. Using OEM stuff and modifying it is going to die in the next 20 years.
Before that.
Probably.
Depends on
racing engines are going to be a very specialized deal.
They are. I mean, you're going to see no one's going to be driving around their race cars anymore or old cars anymore. They're just, it's not going to happen. Let's get rid of it.
And there's another aspect to all this too, because I grew up in a car-centric generation, where cars were something that we looked as art, as this generation doesn't even care.
They don't even care about 69 Mustang or a 69 Cougar. They like, oh yeah, okay, whatever, it's an old car. They don't have that passion and love that I have for this stuff. That's why I'm saying, Gerald Brand, who has a channel, brand racing engines who does some videos. I talked to him yesterday because he has an engine that he's given away. It's an LS engine, and APD is going to supply the carburetor for it. So I was talking with him, and he said, you know what, we need, it'd be nice to have a solidarity where we have a group of guys, you know, that have good YouTube channels, that have good content, that are good, you know, old school guys that can keep this going. And whoever else, I know a lot of people in the industry. In the last year, I mean, I met more people that are I never even thought I would be talking to people like this. Me being just Tim Halstead in his garage playing with his cars. So I have a lot of opportunity to meet a lot of people and bring a lot of people together. And this is something that could happen. You know, I think this is what this craft needs, is a spokesperson. You know, and I'm not saying I'm the king and I'm going to do all this stuff, but I'm just putting ideas out there because 132 people are listening, and this will be on replay, and about 10,000 people will see this. You know, but it would be pretty good to have something like that where we all could exchange information, a collection.
Absolutely.
You know, and that's what I'm doing on this YouTube channel. I'm collecting all the people I can find, get their story, what they can teach me or you guys, and I'm going to file it away, and it's there to look up.
You know, a lot of the future generation isn't like us. There are some out there, though.
There is.
They need to know this.
You're damn right they do. I teach my kids 9 and 12. They're out in the garage. I get it.
How many kids in the future are going to spend 22 years of their life jumping from pro stock team to pro stock team and building engines and dedicating their life to engines? Almost none. So if we can give them some good information,
damn right,
to take this forward. Yeah.
You know, for you guys, now you know when you go start porting ahead, don't go playing around with that short turn. Let it be. Clean up the other stuff. You know, that's what you said. You will. Don't.
Everything's a balance.
I know.
And everything has its place.
You know? Life is a balance, you know?
Life, you know, my job, I've said it millions of times already, airspeed, airspeed, airspeed. I am an airspeed manager. I manage airspeed. That's what I do, you know, and I make the system as efficient as I can and get the airspeeds in line and the harmonics in line. And
that's it. And it all has to match. And that's what keeps all those frequencies and all that mixture where it's got to go.
You know, point in case, we had a C altered engine, 360 cubic inches. This engine had to make peak power. Now, this is before all the engines at the time were making peak power about 9,600. And I knew that in order to blow the index, in order to actually be competitive, it had to make power at 10.1. So I used the math and my experience, and I laid it all out on paper, and I did it. And that engine made 2.87 horsepower per cubic inch at 10,150. Right on the nose, first shot out of the box, which that never happens, by the way. That engine always was like, okay, this works. All my math, all my experience put together on paper, boom, do it, put it on the dyno, and it did exactly what it should do. And it went out and set the record. First shot down the racetrack. Now, that never happens either, by the way.
I know you're running. As soon as you see that thing take off, you're like, okay, what's it going to run? What's the number? Come on now.
I never sweat more. I'm never as nervous more than when I'm standing on the starting line, ever. I have more anxiety standing on the starting line than ever anything else in my life.
Okay, well, get inside the car and see what it feels.
6 months worth of work is coming down to 6 seconds worth of fun.
Dude, I hear you. I hear you. My car took 5 years to finish. I know that feeling. You're sitting in there. Is this going to blow up? Is it going to work? Whatever. That's huge adrenaline. Like this. You know, I love it.
Let's get into the JC51 deal.
Okay. These guys are going to be tripping because there's a whole list of people talking. Yeah, let's do it. And we'll see. We'll go back to the questions then. So if you remember way back, we had done a pro stock video with Darin. That was the last one that we did. And that was 10/14/22. So that was the introduction of the JC51. Now, that said, Jim Cunningham financed this project through Ford Motor Company, Motorsport. So it took a team of guys. We won't go into the whole thing. I'm just trying to surmise it. And Darin was on the job for doing the heads, we'll say. So what we did that time was we presented this engine and how it was developed. And I'll put a link on here so you guys can see this because it's important stuff. I looked at that video. That chat has like almost 100,000 views. So it's good information because, you know, the only thing out there is really the DRCE. It's running down pro stock. So this engine was called the JC51. Now, there was a JC50, which was a Hemi version. We're not going to get into that. We're going to stick with this. So we presented that to you. And when I said that engine made, don't tell me now, didn't I say it made like 1,400, right? 1,400 with a single 4 on a cast intake. Am I right?
No, it's a sheet metal intake, but it's a wet sump with
one
carburetor.
Wet sump. That's what it was. So it's pretty damn impressive for what it makes for horsepower.
499.6 cubic inches. And let me say that
Yes.
Warren was pretty much primary on the DRCE3 as far as helping with the design, and Foltz and I. But I will say that the DRCE3 was not something that we all agreed on. It was something more that the GM engineers wanted us to have.
Now, are you talking the cylinder head or the block?
All of it.
Got it.
And it did not end up the way we wanted.
I understand it.
Now, the JC51 is the exact opposite of that. This engine, they gave us every single thing we wanted, plus stuff we didn't know we wanted.
Now, this is
they used finite element analysis on this block almost $100,000 worth of time just to stress this thing, and took out like 8 pounds. And this thing is so stable. The ring seal is so stable. The bores are so stable. It's absolutely amazing. This is the end result of getting everything we wanted. And the way this engine is performing, I've never seen anything like this in my career. I'm still kind of pinching myself, and I'm very hesitant to predict the future because I know better. But the way this thing is actually accelerating is kind of stunning me. I'm really taken aback. And we'll get into it here in a little bit.
okay. It's an impressive feat without a doubt. You know what I mean?
This engine has everything incorporated into it, you know, like a Monaco chassis. It's all the oil fittings, everything, all the oiling, everything you want. It has zero bearing problems, zero valve train problems, zero any problems. This thing just works. It functions perfectly. I mean, there's been zero issues with it, which never happens.
So to kind of tighten it up, now they made X amount of blocks and heads and parts for this. I don't know the numbers. You may know the numbers. And then Jim Cunningham out of Dian, right? RIP Jim. Yep. But all the parts sat in a warehouse in who knows where for X amount of years. Now this Neff, I'm not sure if he bought it or how he got involved. Someone bought the parts from Ford or whoever. They said, hey, we have all these great pro stock parts. Now what? Well, this is the first running model, so to speak.
Clint Neff and I have been friends since we were 20 years old. So 40 years. And him and his father helped us race our first A Econo dragster and B dragster in competition eliminator. And we became famous friends. And then Toby Graham and a couple of others, we were kind of like the Three Musketeers, you know.
Yep, I dig it.
And he asked me 8 years ago about the JC51, and he asked me, will it be competitive in A dragster or A Econo dragster? And my exact words were, it will annihilate them.
I like it.
And he being my friend and trusting me, went out for the next 4 or 5 years and scoured the United States and picked up every cylinder head and block he could. I think he's got 5, enough for 5 engines. He's got 2 running engines now. They both make within 5 horsepower of each other.
Wow.
And Panhandle Performance is building the engines. They're doing an awesome job. And I just, the performance of the engine is better than I anticipated. Now, what you're looking at here is the K altered that won Indy. This is a JC51 4-cylinder.
So just the cylinder head is on this block, this 4-cylinder block, right? JC51 Pro Stock head on a 4-cylinder.
Yep. Now you're looking at a 600 and what is that thing? It's 250 cubic inches.
250. Okay.
Yeah, and it makes 675 horse. Which, I mean, for a 4-cylinder, it's not like 4-cylinders aren't like V8s. They're going to take a little bit to hit power. They don't have the harmonics in the intake manifold. They don't tune up the same.
Yep.
And they're very difficult to keep from shaking and keep from, or to make a lot of power with.
Okay.
They have a lot of inherent problems. So 675 is what? 2.7 horsepower per cubic inch or something like that. Yeah. That's
impressive, man.
But this thing runs right on the record. I mean, it set the record before, and his daughter, Callie, or I'm sorry, Mazzelli. Yeah, I'm sorry. That's
let me see here. So you're saying the girl that drives this altered is his daughter?
No, that's it's her name is Mazzelli. God dang it. I can't believe I forgot her first name. Kaylee, I think. Kaylee.
There you are. Yeah. Watch out for this.
Yeah.
We're new at this. Okay?
And Neff and the Mazzelli family are friends, and they teamed up to field this car because he built the A Econo dragster, and he didn't want this one to just sit in the garage. So
looks like old Fiat Topolino is what the back looks like.
It kind of does.
You know. All right, let's see. How about this? There it is here. KA Comp Eliminator winner. How do you say that last name? Maurice? Mozeris.
Yeah.
Yep. JC51 4-cylinder, 250 CID, 675, 2.7.
She's a hell of a little racer, I'm telling you.
That must be a handful. There it is right there. Look at that thing, man. Look at that. I bet you that exhaust header is $5,000, you know, time that's spent in that thing. Merge collector.
Now, this is the billet block for it. You can see the 65 millimeter cam off to the side.
I mean, that's an unbelievable size. Look at that thing.
And this is the way drag racing is going right here. If you want to do it, you're just going to have to build it.
I bet when that engine is assembled with that size cam, you could turn it over by hand. So easy, I bet. With that roller, don't you think?
I don't know what the breakaway torque on it is.
And I'll tell you, I bet you would.
Let's see, there's the 1-inch lifters.
That's amazing.
You see how close they are to the deck.
Yeah.
Very, very short push rods.
Stable for sure. What's that thing turn for RPM?
10 something.
Yeah.
It's 10 plus. Now this is the head. This is the V8 being mocked up, but that is the actual JC51 head. You can see the valve rotation and the air through the chamber. It's got a really good path out the exhaust.
So I guess I would call it a rotated valve.
Rotated cannon valve.
Rotated cannon valve. Okay.
Yeah.
I see it. Dang it, man.
And where you rotate those, there's a sweet spot. There's a spot for any engine RPM versus valve area and efficiency.
Yeah.
Where it will tune up, and it is freaking amazing. Because if you rotate them too far, you can knock torque out of the motor. You can actually, basically what you're doing is you're trying to tune the RPM range.
Yep.
Over and above what the valve can feed the engine. So you don't want to do that. You don't want to have more. If the valve itself and the valve efficiency and the induction system tunes up from 94 to 10150 or 88 to 10150, you don't want enough or too much overlap in there that would tune that system up higher, because it's going to make it harder, or lower. You want that sweet spot. If the engine has to operate there, you want to rotate those valves to where they're just right. And there's a problem with over rotating valves too, because when you have a canted valve engine and you rotate the valves, what happens is now you have the exhaust valve in a hole. What you do is you bury that exhaust valve deep into the more you rotate it, the deeper that exhaust valve gets. And what happens is the exhaust flow takes a nosedive. Well, now think about what you're doing. You're trying to increase engine speed and your exhaust is nosediving. Well, you're not going to be able to attain that engine speed. And I don't know what the Johnsons did with their Mopars, Hemis.
Yeah.
They got those things turning almost 12,000. So I don't know what they did. But maybe they went down in intake size and up an exhaust and moved some stuff around. But
I mean, that's why the Hemi's dead in pro stock, man. They cut it down to 10, whatever it is, 10.5.
The Johnsons did more with less than any pro stock team I've ever seen. Man, they were awesome.
You talking about Warren Johnson?
No, the Mopar Johnsons. What the frick is their name?
Can't think of it right now. So when you turn this valve and rotate this valve, you're rotating it clockwise, counterclockwise, correct? Because you're going to hit the wall.
Counterclockwise.
Okay. Yep.
And the whole idea is to rotate it in such a fashion that you don't get that freaking exhaust valve down in that hole. You know, there's a certain point where it starts just climbing into that hole. And there's a sweet spot right there where you get a nice chamber that's deep, you know, and the plug is centered, and you got that nice area over the plug where the combustion chamber efficiency is maximized, and you have all the exhaust flow you need. You're looking at 400 CFM exhaust ports. I mean, and they're small. They're fast. Yeah. They're fast.
I like the taper on that tunnel ram, those tubes. You know, look at that thing.
Also, if you look at how short that runner is,
runner.
That's tuned to 10.1. So peak power is at 10,100. What you don't see is that taper is continued into the port. Half of that runner in the port.
Wow.
It's so short that you have to continue that all the way deep into the port. As a matter of fact, if you see where the two bolts are on the top there of the intake stand, that taper ends about right there.
Okay. Can you see this pointer on here? If I got the cursor on here, can you see it? Or is it just me?
No, can't see it.
Okay. Let's see what else we got here.
Now,
yep.
Now the Neff family fields 3 cars. The A Econo Dragster with the JC51.
Yep.
A altered automatic with a JC51 4-cylinder. Yep. And Callie runs the J Dragster automatic with a Range Rover engine, which I just did a head for, and we'll break that down too.
Range Rover.
Yep. Inline 6. Now look at the power that thing makes. It's
2.8 per cube, man. Come on.
Yeah. That's 4 valves per cylinder.
Nice winning. There you go. Congratulations, guys.
The Neff family sewed it up. Clint with the AED was #1 qualifier.
Yep.
Callie won the comp challenge, and Moseris with the JC51 won the race. Full suite with the JC51.
I mean, just think, what would happen if you put that in a right now a current pro stock car like Quadra Brothers, you know, you took their Mustang and you put that JC51 in there with the same whatever fuel injection, because you have to have it. How do you think that would go against everything else that's out there? How would it compete?
You have to understand these engines, these people have been working on these engines, and refining them to a finite degree for, you know, would it be competitive? Yes, it absolutely could be competitive. That's not even a question.
Got it.
But it needs a proper shop, money, and R&D in order to make it kick everyone's ass. Let's put it that way.
Got it.
You have to have the money and the shop and the 5 guys that are beating on these sons of bitches every goddamn day and burning gas on that dyno to perfect them. In order to put them on the racetrack and win. It's even if it's the best, most powerful engine combination in the world, period, it would still need $500,000, a shop with 2 or 3 guys, and bust an ass every day for 10, 15 hours in order to make it do that. Yeah, this is the range.
The potential is there. Now
the potential is not even in question.
Yep. Man, that would be cool to see Ford back in there with a Ford engine. You know what I mean? God.
Well,
okay, so that's the car.
You know, it's not like when I was there where we had plenty of sponsorship. You know, you had $500,000 of sponsorship a year. The purses were such that, you know, you could, let's put it this way, a shoestring pro stock team could fund its existence and still be competitive. Nowadays, that is not what's going to happen.
Yep.
You have to be wealthy. You have to drop $1 million and you have to spend the time and the money and the energy to do the job. Otherwise, the engine is going to go to waste.
You know, I've been hooking up with that Frank Iconio, and he builds the engines for Christian Quadra. Now, they had 3 pro stock cars at once. You know, I've made videos on it. They're great guys. You know, that's somebody who take this and run. You know what I mean?
You're talking one of the baddest engine builders on the planet.
Frank?
Yeah.
Yeah, he's the best, man. I tell you. We get talking, he's like, just like you and me. I mean, here we are, 2 hours and 36 minutes, 140 people here, and we could do this all night. Not that we're gonna, but this is the call for it. People want to hear this stuff, and that's what I keep pumping it because I want to get it across on this video that people comment on that. Yeah, do something with it. Then I can get you into it, and we'll take care of this.
You're looking at engines that have been built, okay? Not R&D'd.
Yeah.
Built. Okay. First shot. Built. And then they go out there and do this.
God.
I mean, if you had a shop and you could R&D these things, and that's where I got to give Panhandle Performance some heads up, man, because they built a badass engine. I mean, these guys really did a good job.
I'm telling you, way back.
Things doing.
They've been around since at least the early 2000s, because I remember they were one of the premier Ford headquarters back then.
You know, it takes a good engine builder to extract that quickly.
Wow. All right, let's see what we got here.
This is the Ranger overhead that I did. It's 4-valve deal. And that's for that J Dragster.
It does have a short turn, I guess.
Yeah, very little.
Is that a
most 4-valve stuff is over the valve. It's a tumble system. Okay. So the short side itself is almost non-existent in some of these, depending on the engine speed. If you have low engine speed, you have a pronounced short side velocity region there because you have so much valve area. You have way more valve area than you would ever need for a low RPM engine. So you'll see on low RPM engines, you'll see the short side there will be a short side there where here there is not.
Yeah.
And it will be pronounced because that's the choke. That's the high velocity region.
It's all epoxy in the floor.
Half of that head is epoxy. That whole head's epoxy. My God. The roof of it, everything's epoxy.
Well, I saw that all the the intakes right there, all of them have it on the floor right there, right by the valve seat.
The whole top of the ports, everything's filled.
How many hours are in that head?
I didn't really have all that much in that one. I think I had 48, 50.
Oh yeah, look at that.
You
Perfect
notice
example.
the roof is solid epoxy.
All right, how about this? Wow, that's amazing stuff. I'd love to hear what that thing sounds like. Wow. Now, did you make that intake too?
No, I forget who made that.
That's cool too.
I'd like to give him credit, but that's what I did with the valves. The valves were a tulip design.
Yeah.
And I had made some hand ground some tooling to match the radius and everything.
Okay.
And then I ground them down. They're at the base of the radius. They're probably 150 thousandths less material. What I did was with tulip valve, and I just brought it down. And
yeah,
I tuned the back cuts because it has a big throat. So I tuned the back cuts to try to turn the air a little better. So that's what the valves looked like after I was done machining them and swirl polishing them. Now to the AED.
There it is, baby. Clinton F., congratulations.
The baddest AED on the planet.
6.59 at 209 miles an hour, 499.6 cubic inch, JC51, Pro Stock Ford, 2.8 horsepower per CID.
Now, at 2.8 horsepower per cubic inch, that's one carburetor with a wet sump.
The most you can make out of that cubic inch is 1,500 horsepower, right?
Correct.
So, nice. There he is.
That's his first race win. And then he came off this race win and qualified #1 at Indy.
But she's pretty damn happy.
Indy qualified #1. I got to say this. He qualified #1 in the heat of the day with 60 to 70% humidity when everybody slowed down 5 to 800s. The fastest that thing has went is 6:45 at 2:14.
Wow. Amazing. There it is, powered by Ford, baby.
Now, this is the first time that a Ford has ever qualified #1 and won the race.
Yeah, since like 19 something.
83. Yeah.
83. Jesus, Mary and Joseph. Graduated high school in 83. It's a mountain right there.
He built 2 engines, and Panhandle Performance built both of those engines, and both of those engines are within 5 horsepower. It's like 1397 to 1405. That's what they made.
It's amazing. That close. And when you talk about custom, man, that's as custom as it gets, ain't it?
Just about.
What size is that cam tunnel?
That's a 70.
Jesus. What's the biggest? 85 or something? Aren't there some big?
73, 75.
Sorry, guys. We kind of stopped answering questions, but I guess we're just going on to the, look at that.
That's what the heads look like when I get them. Raw castings. See, everything's incorporated. If you look in the upper right and left-hand corners, you'll see some small holes above the bolt holes there. That's oil return. That goes back down to the block.
Yeah, I can
it's routed into the pan away from the crankshaft. So
it drains down the sides.
Yeah, it does not pick that oil up back on the crank.
Okay. Now, what's this block made out of? Is this like
it's a CG block cast by Cat Diesel, which does all the CG stuff.
And that's where they did the DRC1, the DRC1, or at least, well, that's where they did the DRC1. And then that's where they had the problems, Warren said, as they went other places or something. I don't know. And had some problems with the block, as far as like the quality of it. That's amazing. Let's hit the next one. Wow. Yep.
Now that engine right there at 500 cubic inches can turn 11,000 with 274 degrees duration on the intake.
Yeah.
298 on the exhaust with 100 gross lift on both sides.
It doesn't even look that complicated, that valve train, does it? Looks like nothing, you know? It doesn't look that, wow, look at.
Now, when I designed the heads to the springs set down about 350, almost 400 thousandths down into the cylinder head. And the oil is held in the cylinder head. And that that doubles the spring life.
So are they in a bath of oil then, you're saying?
Yeah.
Cooling.
It carries the heat away from the base of the exhaust because they're soaking in oil. I mean, and the oil returns are sized to the point where once you get this thing flowing, that valve cover is an inch full. So they're running in oil.
An inch full of oil.
Yeah.
Wow.
You have to, when you pull the engine back, you have to let it set for a while. Let that valve drain.
Yep.
See how deep the spring pockets are?
Yeah.
Yeah, that was perfect.
300 thousandths, you said?
Yeah. They are bathed in oil. That also helps with harmonics at higher RPM ranges.
Probably absorbs energy, you know what I mean, through a fluid.
Yeah, it does.
Hope these guys are interested in this. There's still always 136 people, so hopefully they still enjoy, because we're cranking out at 2 hours and 45 minutes. Now I see what you're saying. Look at that. I can see where the runner goes into the port right up. I wish I had a pointer that I could point to this damn thing.
Here's some funny facts. Yeah. How much torque does a Pro Stock engine make? In 1996.
Oh, man, you're asking me that.
835 foot-pounds. You know how much it makes now?
What, 835 foot-pounds?
Yeah.
Thought it'd make more than, but okay. Has to make about 1,200.
835 foot-pounds.
Yeah.
It makes the same torque. The runner volume on these engines is about 970 cc's. You know what it was in 96? 960, 760 cc's. The same fucking volume. It's the same volume.
Nothing's changed.
No, but when you shorten the runner, you got to make everything cross-sectionally bigger for the bigger valves and hold that same volume ratio to one cylinder. There's a ratio of volume in that cylinder that you have to hold in order to feed that cylinder. And the torque it makes 1.65 foot-pounds per cubic inch. Every NA engine is limited to that on gasoline. So
say it again.
Every normally aspirated gasoline burning engine is limited to 1.65, maybe 1.67 foot-pounds per cubic inch.
Got it.
So the only way to make more power the same cubic inches is to raise that torque peak higher and higher and higher and higher.
And bring it up. Yeah.
I mean, you're looking at 300 horsepower with the same torque from 1996 to now. Just by moving the power range up.
Now, this is a whole different setup.
Yeah, back.
Now, these are some heads that are made by, and you might even be on here, Robert, Big Head Mower, and so he makes the Assassin head and intakes. Now, these are some heads that, like it says, fit the OEM block and lifter bore layout. Now, I want to say that the ports are changed in order. It's been a while since I've looked at the data. We had talked about it. Darin will fill us in. But you can already see, look at these numbers here. Look at what these things are doing here. Wow. I wish I had a pointer that I could show this to you, but I'm going to go down through here and see what we got. Mrs. DragBoss said hi to Ed's machine. Thank you. Can you run a lighter spring on exhaust? Oh, that's a good question, but that's an easy one for him to answer. You're back. So we were just talking about the Assassin heads that Robert has.
Now, as far as a Ford head goes, or a Ford engine goes, the JC51 was a clean sheet of paper. That design, nothing on that engine will fit or even begin to fit a standard OEM Ford.
Got it.
The Assassin head is a cylinder head that was designed for an OEM Ford with an OEM valve train. Now, you're looking at a set of heads that flows almost exactly what a JC51 does, within 10 CFM, maybe 10 CFM better. But these cylinder heads, even though they flow this amount, will never reach the potential of a JC51 because you can't raise the engine speed higher. Because of the valve train, the OEM valve train
won't go past what?
And the limitations and design considerations we had to make with the cylinder head to fit everything in there around that valve train.
Okay.
So everybody says, well, it's capable of 1,500 horsepower, and it is. The JC51 is capable of 1,500 horsepower. It is. But this is only capable of 1,500 horsepower and like 600 cubic inches. You have to bring the RPMs down to put it in its efficiency range, where the JC51 shines at like 10,200, 10,500. This is going to shine with 650, 630 cubic inches at about 9,000.
So the valve train layout in OEM is limiting you to 9,000.
That and where he had to put the valves.
Yeah.
This is Ed McElmore, by the way, is who designed these cylinder heads. Where he had to put the valves in order to facilitate the rocker arms at a proper plane to operate properly. That is what limits its function as far as engine speed. But it's still capable of 1,500 horsepower. You just have to lower the RPM range and put more cubic inches out there, and it'll do it. Not a problem.
Now, I thought he had told me that they had changed the layout of the ports, intake and exhaust. Am I right?
Yes. Yes, they're reversed.
So is there a picture? Let me see what's next for the pictures here.
They're reversed from a normal Ford. So you have to have a custom billet, which they make them. It's not an issue.
Yep. That's the cylinder head there, correct?
Mm-hmm. Now, when I saw this, I got to tell this story because
let's hear it.
Still blows me away. I met Ed McElmore at PRI.
Yep.
And I was looking at this cylinder head, and I stood there for I don't know how long. I think it was probably an hour. And I came back like twice, and I kept looking at it, and I kept looking at it.
What's wrong? Yeah.
And I'm like, he did every single thing that I would do, plus some. So then I started talking to Ed. Ed is not a cylinder head designer. This is one of the first heads he's ever designed.
Yep.
What he did was he went to all the engine builders and asked them, what do you hate about this? What should I do? What do you think I should do here? What do you hate about this cylinder head and that cylinder head? And he made pro and con list and went through and designed this thing. And there's not one damn thing I'd change on it. It's amazing.
And I'm working on a video that's going to show you guys exactly how this came to be from the beginning to the end. So it's going to be a cool video. Look at that.
This is the nitrous chamber. This is recessed plugs and big chambers. And later on, the next pictures will show you a really small chamber. But that's a big-ass chamber.
Look at that intake. How many cc's is that? What's the volume of that runner?
I don't know. I don't think I've CC'd the damn thing. The cross-sectional area is really all I care about.
You can pour a lot of fluid in there. That's for sure.
This is also a manifold he came up with.
Wow.
And this is a lower RPM engine. It's got longer runners for
right.
64.
Very beautiful.
Now this is the small chamber.
How many cc's is that? Like 40 or something?
47.
Yeah.
You see how far the intake is off the bore wall?
Yeah.
There's a lot of flat over there, isn't there?
Yeah.
If you notice,
thousands, it looks like.
if you notice how tight that chamber is over there on that side,
yeah,
there's a reason for that. Because there's less airflow over there, so the chamber needs to be tighter to hold the airspeed up. If you put a velocity probe around that valve, you'll find that that chamber wall is tuned to bring the velocities as close together as I can. So if you laid that wall back, you would dump the pressure too fast. The velocity would take a dump. Well, guess what reversion is going to act on first? It's going to act on the low velocity area. So if you keep that area over there tight and fast and move it off the bore wall,
yep,
and try to get the airspeed around that valve as even as you can, home run. I see people lay chambers back way too far a lot. And that's another area where the flow bench will lie to you. Because you can lay a combustion chamber back and gain like 5 CFM down low and think you've made a gain and lost probably 25% of your pressure recovery out the valve.
See, this is where it gets in depth, man. I'm telling you. 600. I mean, this is crazy. 400 exhaust. Wow.
That's a 2585 intake and a 1850 exhaust. Remember when I said that 118 CFM per square inch valve area is your target?
Yep.
Look over here in the second to left column, CFM per square inch of valve area, where it hits 118 at 1.1.
Yeah, I see.
I would like to have it hit 118 at 1. That would be my preferred place. But you also see it hits 120. It takes a spike up. Now, ports, 2-valve ports are really weird about that because at a certain point, you have the Venturi convergence point where the curtain area and the throat are the same. And then at another point, which is 0.45 lift to diameter ratio, where the valve is so out of the way of the port that the port doesn't even see it. And that's what happens when you exceed 118 CFM per square inch of valve area at the higher lift regions. As a matter of fact, you'll see the flow curve come up and level off and then shoot up right at the very end. When in the 1.1, 1.2, 1.3, 1.4 range, all the way up in there, it'll continue to go up. That thing will probably move 640 at 1.350. It'll keep going because the valve, the port doesn't even see the valve is in the way at that point. It's just the port. That's the secondary convergence point.
How much lift are these cams using? How big are these cams?
Pro mods are in the 1.350 range. And normally something like this will see 1.150, 1.180.
So it would respond. This was what, 655 cubic inch you said, or 650?
Yeah.
Right? Let's say you put it on 700. It'll adjust accordingly and make more power by the virtual increase in size in cubic inch, correct?
Correct.
Obviously, right? Is it designed for a certain cubic inch motor?
Well, if there's a certain cubic inch of engine to hit an individual RPM range, whatever that is. So it's if it's 500 cubic inches, it can make 1,500 horsepower at
10.5, whatever.
10.2.
Okay.
If it's 600 cubic inches, it'll make that 1,500 horsepower at 92.
Yeah.
If it's 700 cubic inches, it'll make that 1,500 horsepower at 82, 85, somewhere in there. But the flow potential is 1,500 horsepower. The more cubic inches you stick under it, the lower the RPM range will be.
I think that's all she wrote, brother. That's
How
all.
long have we been talking? 7, 8?
It's only been 2 hours and 58 minutes. That's it. You know?
Only?
Yeah, that's it. Now, how do we get back to where we were? Let's see. There we are. But let's run down and see, and because My eyes are starting to dry out now. I can tell my contacts are like starting to be here. Because we said we were only going to talk at the most 3 hours, and that's about 48 seconds away. So I want to see if anybody else had talked. And we'll have to just revisit this because there's so many people that want to ask stuff. So that's what we're going to do. Yep, people are saying the same thing. Hey, let's hear you again. Can you do this again? Can we do that? Blah, blah, blah. So let's do this. This is how it's going to work. You and I will come up with a plan. I'll figure out how to do it on my channel. We'll come up with the first thing you want to discuss, a topic that you think is pertinent. That's why I asked that thing on cross-sectional area. I didn't have a great understanding of that. I think you need to get what basics they are and start from that, and then we carry it on.
Yeah, I can do a whole outline from the combustion chamber to the throat right on out, and just do the whole velocity profile of how the induction system is tuned. That's not a problem.
That's what we should do then. I think it'd be good. Let's see. Just trying to run down through, make sure I didn't miss anybody. I don't want to forget people that contributed. Daniel Wilson, thank you so much. 1999. Tim and Darin, how about a cup of coffee? My treat. There you go. Thanks, Daniel Wilson. We appreciate that. I don't want to forget people. Roland Tamacchio, you said you knew him, didn't you? Did you know him, Roland?
Yep.
He's back in there. He should be on here and telling his story. So let's see, Sean, there you are, inline inductions. He does a lot of 6-cylinder stuff in Australia. He was asking about the Barrowhead. Have you done Barrowheads?
No, I haven't, and I look forward to doing so. I've talked to people about it, and I'm really interested in that platform.
Sean supplied me with a bunch of pictures on the port work he's done and the numbers. I'll make a video on that someday because I like that cylinder head. It's impressive. Let's see, what else do we have? We're going back through. Everybody says thank you. They appreciate it. And I thank you guys, man, for being here. Like I said, everything that's donated on this live chat, because you can donate after it's over, all goes to Darin for his time to help us so we can get a better understanding. And we'll set it up on DragBoss Garage where you can have private access, get your questions answered, and get the time, because I know I missed a lot of people, and I'm sorry, but 3 hours, like I said, couldn't you talk, Darin, for another 4 or 5 hours? Probably another 3 at least.
I've conducted 65 classes on induction system research and development, and I speak for 10 hours a day for 2 days.
Okay. I could do it too, but my wife's in there waiting for me, and I ain't going to give that up. So boys and girls that were here, people that stopped by DragBoss Garage, I appreciate it, because like I said, knowledge is power, and that's what I'm trying to give you, the knowledge you ain't going to find nowhere else, so you can have your combination that you want and perform the way you want. And that's what we're doing here. So we're
I got to say something about that too.
Go ahead.
This is the information age. And, in my day, when I had to learn something, I had to go to the public library. I had to get in my car, drive to the library, read a whole bunch of books. And if the book that I didn't need wasn't there, I had to go to the college library. So now you can look anything up. But the problem is it lacks context and nuance. Because every situation is different and calls for a little, the basic rules I can teach, that's not hard. But every situation is a little different, and you have to utilize all those rules and come up with a game plan for that particular engine. You know what I mean?
I do know.
It's all lost today. Experience. You can gain the knowledge, but you can't get the experience.
That's exactly what I said. You're right on it, man. That is. And that's what you're getting. 40 years of experience of you doing this, saying, look, buddy, this is what's going to happen if you change that valve size or you do this. That saves someone a lot of time and money, and it teaches them a lesson. That's the point that we're trying to do, is Darin is trying to give back his knowledge, because you know what? All the stuff that we have, like I said, it's just stuff. But some of it ain't stuff, and some of it we got to give back. And this is how we do it, is by doing this for you, so that you can learn. And whether you're a professional head porter who cares? I don't care what you do. If this competition, this is free sharing of information. This is how it works. So put your ideas on here. If you want to join this group, it's not going to be free. I'm going to tell you right now. The time that we put into this, just to be a YouTuber, it takes a lot of time to do these channels and make them successful. And bring you stuff that's good stuff, not just boring stuff that you see anywhere else. So we'll figure out how we're going to do that. It'll be like a membership here. I never had a membership here, but maybe we'll have that be the membership, and we'll figure that out. It's coming. So with that, we're going to say good night, everybody that stopped in. I appreciate you being here, as does Darin Morgan. So stay tuned to DragBoss Garage.
Thanks, guys.
Ian.